Okay, so let's ask a question. What does a binary code look like?
Zeros and
Come
ones.
on. Zeros and ones, right? Okay. All right, and you can do stuff with binary. You can do stuff with zeros and ones. You can, for instance, you can say, okay, well, here's a word and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 characters, let's say. Say, okay, let's count the number of odds. 1, 2, 3, 4. There are 4 ones. That's an even number, so we're going to put a 0 at the end. So this is our parity check. Looks for a comparison of the first 13 bits to tell whether they're even or odd. And then if we get an odd number, that means something was wrong. We made a mistake. So that's the simplest way to do it. So, okay. So now how do we actually encode this? Well, we can send over the radio, we can send, like if we were to look at the frequencies, we can send either this frequency, we'll call that a 0, or this frequency, and we'll call that a 1. And we can go, or in time, as our time goes that way, we can go this one, then this one, and this one, and then this one, and this, and this, and this. So basically we can track what our zeros and ones are, right? We could basically listen to it and hear it go. That's a binary code. There's also other ways to do this. So let's say we take this 2 bits at a time. 1, 0. Anybody know what that number is in binary? What does that translate to?
2.
That's 2. How about 0, 0?
0.
0, 0, 0 is 0. 0, 1 is 1.
1.
1, 0.
2.
2. 0, 0 is 0, and 0, 1 is 1. So now we could send this as 1, 0, 2, 1, 0, 0, 2, where the whole alphabet is 0, 1, 2, or 3. We didn't see any just because I didn't make the code very well. But now we can do this. So we have 0, 0 is here, 0, 1 is here, 0, 2 is here, and 0, 3 is here. And whenever any of those happens, we're going to make a shift to that point. So here's a 1, and then here's a 0, and here's a 2, and here's a 1, and then a 0, and a 0, and a 2 over time. And that is basically is very close to what we were just seeing when we were looking at that digital data. So it's a kind of a modified format of sending a digital code. Let's see, let's go back to WebSDR. I'll go find a digital code. It's kind of cool stuff, actually. That's just doing it really fast. That one's a lot slower. And you can actually see those dots moving around on the screen, each of them representing a different number, which represents a different piece of data.
I was late.
We haven't started yet.
Yeah. WebSDR, is that local to Eugene?
Oh no.
Okay. No, I'm saying, is that like, are you listening to something local? Because I have the SDR radio that I've screwed around with, but could you listen to the stations that are in Eugene on that?
I mean, I suppose if you could hear them.
Oh, okay. I mean,
I mean, think of it as this is somebody's receiver somewhere with a whip antenna that's just near their office, house, school, whatever.
okay.
And they put it on the web, and people on the web can basically run their radio
Got it.
and listen to it and make it do different things, which is why sometimes I like going to the northern Utah one, because it's about, 700-800 miles from here where I
Yeah.
live. And depending on the band I'm on, I can actually take a listen to myself, see what I sound like. In other words,
Awesome.
I transmit on the air on 40 meters and I hear my own signal being picked up. And then I can listen to it over the computer and say, oh yeah, my audio sounds fine. Or no, my audio is all distorted.
So when you say a whip antenna, and forgive me, how large
It could be
of a
anything.
setup?
I mean,
Okay.
if you're not transmitting with it, it could be literally anything.
Okay.
So. All right. Well, I started recording and it's 9 o'clock. So people are a little slow getting here, which is fine. Doesn't bother me. Just so long as like half the people don't drop out, then we're okay. Then I'll just take it as a personal insult. So, all right. Does anyone have any questions from yesterday? Nothing?
A
Not a
lot
thing?
to take in. A lot to take in. It was.
Yeah. Okay. We're going to do a lot more different stuff today. But are there any specific questions from yesterday that you're just like, I really want that answered, and you think that everybody else could possibly want it too?
I don't have any questions specifically, but I did really enjoy learning how a microwave worked. And I feel like there were like 4 other things yesterday I took to my partner and I was like, oh my gosh, I learned how this worked today. I learned you
Yeah.
can bounce things off the Aurora.
Oh yeah.
So far, so good. This is awesome.
Hey, did you go and bother Andrew?
No, I didn't.
Got to remember to do that.
And I'll be in the rocket room today.
It's fun to bother him.
It is. You're right.
All right. Any questions? Anything you've got? Now is a really good time because people are still rolling in.
I got a question.
Okay.
So I just been doing some research on like radios. And I was wondering what your opinion was on like a good like beginner radio. I mean, I think I've been looking at some of the Baofangs and I think that's probably what I want to go with, but I just wanted to ask what you thought. Don't do that. Okay. I mean, I'm used to like, figuring out how like fiddly complicated things work. So I'm not afraid of the learning curve, but
No. Well, there are several reasons why I say don't go the Baofeng route.
Mhm.
All right. The Baofeng, there's nothing inherently wrong with the Baofeng, but we're going to learn about this too. This is actually a great segue. Okay. So
cool.
Let's say we have a black box, which is a receiver, and we hook up this black box to an antenna, right? What do you expect that the receiver will do?
Just take in the information from
Right.
the
It's going to
antenna and
receive.
output it.
It's going to receive, right? And you're going to be able to listen to it. Okay. So let's say that the frequency range that this antenna is exposed to is from 0 megahertz up to 0 hertz up to infinity megahertz. That's true. It is, right? The antenna, in theory, can pick up literally anything. So whose job is it to discern between different frequencies?
The operator.
No.
Hmm.
Look at
Oh, discern between, the receiver.
the receiver. Yeah. Okay. So let's say the receiver, you want to tune it to 144 to 148 megahertz. All right. So what is it the receiver's job to do at that point? To all the frequencies outside of that range.
Oh, to filter them out.
Yeah. Basically, you want to eliminate those filters. Now, inside this receiver, what you have is, we'll make it an amplifier stage, right? That's a block diagram. That's a block diagram for an amplifier. All right. So how much power does an amplifier have to amplify? And Daniel, I should have sent everybody an email with a YouTube link yesterday afternoon.
Mhm.
So did everybody get the YouTube link via email?
Yeah.
Okay,
Yes.
good. And it was, and the audio, like I said, I hate the sound of my own voice, so I think it worked. Okay, so let's ask the question, how much available, how much ability does that amplifier have to amplify everything that it hears? Well, if it's a real wideband amplifier, everything that comes in is going to get amplified, right? So what if there's another signal? Let's say there's a bunch of signals in this band that you want to listen to and some really big ones over here. Where is most of the power, if there is no filtering, going to be dealing with amplifying, even though you didn't want it to? Those big signals are going to take up most of the receiver's amplifying ability. So what's going to happen to these little things in there, which are the things you actually want to listen to?
Well, they get drowned out.
They get drowned out. That's right. You basically use up the amplifier's ability to amplify on the stuff that you didn't care about in the first place. This is known as desense. And what's a way to avoid a desense situation? What's the easiest way to avoid this desense situation?
Just to decrease the I guess the frequencies that you're reading on.
Yep. And that is called filtering, where you basically have a band pass filter where you want it to be. And it basically allows the frequencies to get through that you want, and it rejects the frequencies that you don't want. The difference between, let's say, there are two radios that are basically built on the exact same chassis. There's a Yaesu FT65. Is it the 65? Or is it the VX? We'll say it's the VX4DR. And the Baofeng anything. Anything Baofeng makes is basically the exact same radio in a different package. This costs between $25 and $40. This costs $85 to $90. This is the exact same chipset. It's the exact same RF amplifier. It's the exact same battery that does the exact same job with the exact same antenna. What is the difference between the exact same radio if you have a difference in price between $85 and $90, assuming that the Yaesu is just going to be a little more expensive because it's, it's a little more expensive brand than a Baofeng? What is the fundamental difference between the 85, 90? Nope, the battery is all rechargeable. Batteries are always the same.
The antenna?
Nope, antennas are the same. Component quality is basically the same. They come out of the same factory in China.
So is it the
Not the brand name.
parameters of the two radios are different?
Nope, not the software. Well, the software is a little different, but software is
The hertz?
basically free.
The hertz it uses?
Nope, they receive the same thing.
Filters?
Filters.
Its range?
Nope, right there.
The quality of the components?
Nope, components are the same. The difference is right here. Right there, the filter. The filtering on the front end of the radio. What happens is that a Yaesu has a decent filter and a Baofeng essentially has no filter, which basically means you take the Baofeng out into an RF quiet environment, it'll work fine. As soon as you get it into an environment where there's any kind of RF floating around, it becomes desensitized and doesn't work. There you go. That's it.
Oh, I do actually have a question.
Yep.
A friend told me once that the question pool for the general exam was very similar, if not the same, to the technician pool.
I might have said that.
What was that?
I might have said that too.
Oh, really?
Uh-huh.
Wait, well, then what are your thoughts on it? Because I actually would really like to take my general exam, and I've been
Okay.
studying to be off with this technician question
Okay.
pool. Wasn't sure if that was.
If you understand the physics and you understand the math, right? If you have a good understanding of the physics and the math, the only difference between the general and the technician is the fact that now we go back to the general class license. And what I'm going to do is pull this up somewhere here. I had to close my packet from yesterday. Here we go, band plan. The only difference really fundamentally between the general class exam and the technician exam, because I go way above and beyond what you really need to know for the technician class license, is that the technician license gives you this little swath, this little green, the little green hatch down here on 80
Mhm.
meters. It gives you the green hatch on 40 meters. It gives you the green hatch on 15 meters, and it gives you the blue hatch on 10. General gives you some part of every frequency band on HF. And you're also allowed to be you can also, as a general, you can give technician class license exams as a volunteer examiner.
Oh, nice.
If you are willing to take the extra effort and go through the general class pool, the electronics are a little more complicated. The propagation stuff covers the high frequency bands and long distance communications and power limits and data rates that are used on the HF bands and stuff like that. If you're willing to go through and spend a couple of days studying that also, if you take one exam and you pass it, they will ask if you want to take the second exam, if you feel comfortable doing so.
Cool. Is
And
the
it's
general
free.
question pool as available as the technician one is? Like,
Yep.
Is it a print?
All the same tools,
Oh, great.
same number of questions. So what I found is that if somebody goes through this that we're doing and gets to the technician exam and does really well because they have a really good understanding of the theory and figuring out antenna lengths and stuff like that. It says that the Zoom link is invalid for today. Did anyone else have any problems?
We're all here, so no.
Nope.
I
Well,
didn't.
you know,
I had computer problems myself, so I just now got on.
I used the new Zoom link that you sent today. I didn't try the old one, so I don't know if the old one worked or not.
but you're obviously here. So
Yes.
I tuned in at 9 a.m. Pacific, and class started a little earlier. Or?
well, no, I just happened to log in earlier.
Okay.
Okay.
Do you think we need to look at the ARRL book to study for all the tests?
No, my kids never cracked that book at all.
Okay. It's awfully spendy.
It is, yeah. I mean, the question pool is the question pool. You know, it's public information. And personally, I'm a big fan of that iPhone app because you can study section by section. I mean, I know people like my wife who don't know a thing about electrical stuff at all. And she's got her technician license because she's really good at studying. Hold on, let's see. 1 second.
Which app are you talking about, Scott?
Ham radio exam -tech.
Ham radio exam?
Yeah.
Okay, so that's an app, right? So
Yeah.
just check it out and go from it. How does it look? Any idea or
yeah, hold
what
on a
was the
second.
icon? Sure.
I'll open it up on my phone.
It was in the link. To the
It was,
app was in your
I included a
email.
link for it, yeah. It looks just like this. Can everyone see it?
Okay, technician, yeah.
Yep. It's ham radio exam dash tech.
Okay,
And it's very well written. And my kids used it. Actually, my kids and my wife used it for all their exams. So, and they're free. You can't beat the price. So there you go. If you're looking at getting a general class license, go a little bit further. And oh, what I was saying is that of the people who, if you go through and let's say you really kill the technician exam, even if you've never looked at the general exam, you'll get 50%. And you need 74. So all right, any other questions?
I just have one quick question for you.
Yeah,
So I went ahead and I'm taking the exam on Friday.
okay.
And I paid for the one exam for $15. Would I have to
Mhm.
notify them if I'm looking to take both exams? Or if
Nope.
I pass the first one, they'll automatically ask me if I want to take the second one?
Or you can just say, hey, I think I did really well. I'd like to take the general.
Okay, perfect.
If they
Thank
don't
you.
ask, you can always ask that. I mean,
Okay, thank you.
our goal is, our goal is to get you there.
Sure.
So,
I appreciate it. Thanks, Scott.
Do
All
we get
right.
notified if we pass on the spot?
what?
Do we get notified if we pass? Is it on the spot?
Basically, as soon as you're done and you hit grade exam, it'll grade your exam and you'll get your score.
Cool.
A little bit of history. Way back when you actually, did anyone here hold a license in the past? I'm
Yes,
just curious. Who was that?
Chris Wilson.
Okay, about what time? What years?
I took my test in 98.
98. Okay, what class did you have?
I was a general radio operator.
All right, but did you hold a ham license?
Negative.
Okay. All right. So it used to be that when you went to go take your license exam, before about 1982, you actually had to go to the FCC office and you went and sat for your exam and you took a code test. And if you didn't pass your code test, they just sent you home. You never even got to take the written exam. If you passed your code test and you took the written exam, you wouldn't know for at least a month whether or not you passed it. They wouldn't even tell you. So either you did or did not get something in the mail.
We had local people from Anchorage come down to Seward and grade our test on the spot, and
Right.
that was a real bonus, an added bonus.
Well, like I said, before 1982. So, but that was the way it worked back then. So, all right, here we go. Let's start doing electrical stuff. All right. So if we have no more questions about propagation and stuff like that, which we're going to be getting back to just because at some point we have to, what we're going to start covering is electrical principles. Okay. So Ohm's law. In order to understand Ohm's law, we need a couple of different things. We need letters. We need an E, we need an I, and we need an R and a P. E is also sometimes represented as V or volts. E is electromotive force. I is current, that's measured in amps, which is the movement of electrons. R is resistance measured in ohms, which is the property of something to resist the flow of DC current. And then we have P, which is power, that's measured in watts. And that is basically a rate of consumption or generation of energy. Now, we also have another one. We have something called X, which is reactance. That's measured in ohms. That is resistance to AC. And then we have Z, which is also measured in ohms, and this is known as impedance, which is a resistance to the flow of AC. So clearly we're going to have to go through and we're going to have to create some of these things in your head. And to get an understanding of, okay, well, we've got a lot of letters here. Well, it turns out we've actually got more too. We've got C, which is measured in farads. That's capacitance. And then we've got L, which is measured in henries, which is inductance.
You're off the screen. We can't even see where you wrote L.
Oh, did it disappear? Should be right at the bottom. I'll put it up
I
at
can
the
see
top.
it.
I'll put it up at the top. And that's in henries, that's inductance. Okay. So there we go. There's our basic units that we're going to be using when we deal with Ohm's law. And I think what I'm going to do here is I'm going to just put a line over here. I'm going to work on the right-hand side. Okay, so Ohm's law. Ohm's law is E is equal to I times R. That is Ohm's law. Electromotive force is equal to current times resistance. But now we actually have to go one step further. We have to say, what is current? So now what we have to do is we have to go into our atoms and we have to draw our nucleus. So we'll make a carbon atom. All right, so that has 6 protons and 6 neutrons. And zipping around this carbon atom, the protons are positively charged. We have an electron, and those are actually in the first orbital. And then on the second orbital, we have 4 more. So we have 2 electrons here and 4 electrons here. So we're neutrally balanced, and we have the same number of electrons and protons in that atom. So it's a neutral atom, but notice we have these electrons and they're kind of far away from the nucleus. Well, the bigger the atom gets, the farther those far electrons are from the nucleus. And also the fewer electrons in that outer ring, potentially the easier it is to pull one away. If something is easy to pull an electron away from it, that basically means what we end up with is a metal. And if we have a metal, that means that basically, let's draw, for instance, copper. I'm not going to draw the whole copper atom because it's got a lot of electrons in it and a lot of protons. But what we're going to do is have a nucleus, and then we're going to have a couple of electrons that are kind of loose. And we're going to have another copper atom here with an electron and another one. And copper is such that as an electron floats into the area, what'll happen is that it will temporarily join this copper atom, and this electron kind of pops out and joins this copper atom, which causes this one to pop out and join this copper atom. And then you end up with something which looks like the flow of electrons, where every electron that comes in is matched by an electron flowing out. If we were to take this in a piece of wire instead, what we would have is a bunch of copper atoms. And when we have an electron that floats in, we have an electron that comes out. Movement of electrons from one place to another is known as current. The resistance, the intrinsic property of this material to resist the movement of electrons through it, is known as resistance.
What was that last part again?
The intrinsic property of being able to resist the flow of electrons through a material is resistance. Something that allows current electrons to flow is a conductor. And something that resists the flow of electrons is an insulator. So let's hear some examples of things that are conductors and some that are insulators.
Copper, aluminum,
Aluminum's good. Another one?
Brass.
Brass, good. Other ones?
Glass is an insulator.
Glass is an insulator. Yep. Other ones?
ceramic is an insulator.
Ceramic is usually an insulator, although it can be a thermal conductor and a and an electrical insulator, depending on how
Gold.
it's built. Gold. is a
Silver and
really-
gold.
Silver and gold are really good.
Steel.
Steel is okay. It's metal. How about like sodium?
Oh, that's true.
Actually, sodium's pretty good.
Yes. 'Cause,
Okay, how about some more
sea-
insulators?
Seawater as the
Mhm.
conductor.
Well, in particular, because it's ionized.
Hmm.
Seawater is full of ions.
Paper.
Paper is actually a really good insulator. Other ones?
Oh, wow.
Concrete.
Concrete is okay, yeah.
Glass.
Glass, yeah. Other ones?
Plastic.
Plastic.
Anyone say rubber yet?
No one said rubber.
A circuit board.
Fiberglass, yeah.
Wood.
Wood's pretty good unless it's wet or soaked in or soaked in salt water. Actually, water is a really good insulator. Unless you put salt in it. Fresh, like deionized water is actually a really good electrical insulator. How about one more? I'm moving my hand through it.
Yeah,
Air is actually a really good insulator, and it's a good thing too, because otherwise those power lines that were hanging would short out. So air is
What
actually
about-
a really good insulator.
What about oxygen?
Oxygen, yeah, because it's part of air. That combination of oxygen, nitrogen is a pretty good insulator. So let me ask this question. What would make air not such a good insulator?
A lot of moisture.
A lot of moisture, and in particular,
Ions.
rain.
rain, or what else? How about if you live near something?
Vegetation.
Now,
Salt.
salt water. Yes, if you live near the ocean, the air is actually quite conductive. Yes, someone said humidity and salt. So there was a de-expedition that went to I think what was it, Norfolk Island or Chatham Island in the South Pacific. It's owned by New Zealand, and they kept having these problems where they'd never had problems before, and they kept burning up their ropes. And what was weird was that they only burned up the ropes on the antennas where they were using the ropes to hold their wires. And what would happen was that the ropes would pick up salt water from the air and become conductive, and then they would conduct electricity and it would turn into a fuse and go poof. Suddenly you had conductive rope. So anyway,
That's cool.
it's kind of interesting, isn't it? Okay, so what we're going to do now that we understand the difference between conductors and insulators, is we're going to have a source of electrons. A current is the flow of electrons through a point. So what we're going to do is we're going to create a battery which has a source of voltage. That source of voltage, what would this be called if I just connected this battery to a piece of wire which had no resistance?
Closed circuit.
That would be a short circuit.
Oh, short circuit. Yeah.
That would be a short circuit. And so the battery would basically generate its voltage, its electromotive force, and push it through a piece of copper. And what would happen to the copper?
It would melt.
Yeah,
It would probably melt, exactly. Or it would burn up your battery, or both. So not something you want to do. So what we do now is we add this thing called a resistor. A resistor is a device that resists the flow of current. And a resistor has something called resistance, which is a measure of how much it fights back against the flow of current. So by convention, our current flows out of the positive and around the circuit and back into the negative. You may notice the word circuit. We're on a racetrack. That's known as a circuit. Also comes from the word circle because it makes a complete loop. Okay, so now we have our current, which is our letter I. It's measured in amperes, named after ampere. Our voltage is named after Alessandro Volta, and our resistance is measured in ohms, named after Georg Simon Ohm. Notice those are all 19th century scientists who worked on this stuff a lot. So what we have now is we have a voltage, which is an electromotive force. In other words, being able to move electricity through a resistor. And the end result is the amount of current, the flow of electrons that are actually pushed through the device, which is the resistor. The relationship is E is equal to I times R, which is Ohm's law. We can also write this as E, I, R, that same circle. And the great thing about it is if you can't remember what to do, you can always make the circle. So long as you make the circle right, then you'll be okay. And as soon as you get your scratch paper, you can make your circle. So let's say that in this particular case, what we're going to do is we're going to say that we have a voltage of 6 volts. This is a lantern battery. And we have a resistance of 6 ohms. Okay, so what's the thing that we don't know? We don't know our current. So we're going to put an X through the current, and we have our current is equal to E divided by R, which is 6 divided by 6, which is 1 amp. 1 ampere of current. Now, that doesn't necessarily sound like a lot. This is actually about 1.6 times 10 to the 19th electrons per second flowing through any given point. So in other words, that's 1/6000000000000000000000000 electrons every second. Electrons are really, really small. They don't carry a lot of voltage. They don't carry a lot of anything. They're really tiny, but they do exist. So it's like a massive flow of electrons. Okay, so now what we're going to do is I'm going to ask this question one time and one time only, and then we're going to forget I even said it, but it's important to know. What is the charge on an electron, plus or minus?
Minus.
Minus. Well, which side of the battery here do you think it should be coming out of, the top or the bottom?
Bottom.
Yeah, probably out of the bottom, right? By convention, current, even though current is the flow of electrons, comes out of the plus. And that is because somebody made a mistake before electrons had even been discovered. They knew there was this thing called a battery with a plus and a minus terminal, but they didn't know that the thing that carried, the particle itself that carried the charge was actually a negative charge, which flowed that way. So they didn't know that. We still live with that mistake. It's important to understand it, but from now on, we're just going to say, you know what? Okay, it was a mistake. We're going to go with the fact that that current flows out of the positive. Okay, so now what we're going to do is take this battery and we're going to replace that battery with a 12-volt battery. And why are 12-volt batteries important?
Car batteries.
Yep, car battery is 12 volts. Okay. And in particular, if we were to look at a car battery over time, we have our voltage and we have our time, we would find that the voltage is about 12 volts. Really, it's about 13.8 if it's fully charged. But we would find that it was this. It was always the same voltage at pretty much any time, which means that the current that it generates is always going to flow that way. This is known as direct current. Now, if we were to take a voltage source, which instead of a car battery looked like this, that is a sine wave. So for the first half of the period of a sine wave, this is the plus part, and the second part is the negative part. Well, during the plus part goes there, so the current would flow this way. But then when it gets down to the middle, that center point, we actually go across a 0 point, which means that when it's 0, we have no voltage at all. Then when we get to the bottom part, we have a plus here and a minus here, and our current goes this way. And this is known as alternating current. So now here's an important question. Does a resistor care which way the current is flowing?
No,
Does it make any difference to the resistor?
nope.
Nope, makes no resistance at all. Now, notice on the left-hand side, we're actually going to get rid of reactance for the time being. We're just going to put some X's through it. We'll get back to that. So now for this particular circuit, we know that in a resistor, R for a resistor equals Z for a resistor. Does everybody agree with that?
Yeah.
If a resistor has a certain amount of impedance for AC and for DC, and it doesn't care which is which, it's always going to have the same property. So for a resistor, our R, which is our resistance, is equal to our Z, which is its impedance. It's going to have the same number of ohms. They're going to be equal. Which actually, for the case of doing calculations like this, it makes it really, really easy because we don't care what the voltage looks like exactly. So the next thing we're going to do is we're going to create a battery again, or a power supply, or whatever it happens to be. We're going to say that this is 12 volts. We're going to say that this is DC. This is our car battery again. And why are 12 volts? Why are 12 volt power supplies so common?
It's
in-
what
in
most
the
of our ham
radio world?
radios operate off of.
That's right, because most ham radios are designed to operate off of a car battery, because a lot of things are designed to be operated out of a mobile vehicle. And so the way to replace that is that you create a 12 volt power supply, which can run a radio that could be operated in a car inside. So 12 volts DC is kind of a de facto battery, de facto power supply that all radios use. And that's why we do that, because of car batteries. Okay, so let's say we have a 12 volt power supply and we have a 1 ohm resistance. Okay, so let's go through the calculations. This is Ohm's law again. E
12 ohms.
I R, like that. Okay, and we don't know our current. I is equal to E divided by R is equal to 12 divided by 1. And this is actually volts, and this is ohms. And this is 12 amps. Okay, so now this is actually the next step. We're going to use the second part of Ohm's law. So we know that our current is 12 amps. Okay, here's the next part of Ohm's law. We want to know how much power. Oh, go ahead.
I said you erased it before I could write down the notes of the first part.
Which one?
Ohm's law.
Well, E equals I times R. And P equals I times E.
Yeah, put
Actually,
the,
I might as well write them up here. P equals I times E. E equals I times R.
if you can put those numbers in there again, the 12 volts over 1.
Oh, yeah, okay.
Yeah, that's a simple formula. Thanks.
E, I, R, like that. And in this case, we don't know the current. I is equal to E divided by R is 12 over 1 is 12 amps. Okay, so now what we're going to do is figure out what the power is that is being dissipated in the resistor. So what we can do is we can play around with this a little bit. Well, let's take a look at the power in the power supply first. Well, because we know that the power supply is 12 volts. And the current is 12 amps. So we have P equals I times E. And by this, we don't know the power. So we have I times E. Power is equal to 12 times 12 is 144 watts. Anybody argue with that?
I'm not gonna argue with it, but it's a little fast for those of us who are slow under the hat with mathematics.
Well, we'll do it again. We're going to do it again. We're going to do it several times. Okay, so the next thing that we can look at is say, okay, well, we're going to look at the resistor. And here we start to look at, see, we can do this a couple of different ways. Intuitively speaking, if the power supply is supplying 144 watts, how much should that resistor be dissipating? If the power supply is putting 144 watts into the circuit, how much should that resistor be putting out?
1 ohm.
No, power. How much power?
I guess 144 watts.
144 watts. Yeah.
There's
Okay.
no other work being done.
That's right. Okay. Now it's important to cover this, that power is energy per unit time. That is what power is. That is the
Energy-
definition of power.
Energy what now?
Energy per unit time. So if I were, and energy is measured in joules and time is measured in seconds, and 1 watt is a joule per second. It's basically an amount of energy per unit time. So let's say that I have a black box. Okay, if I erase this,
1 joule per what?
1 joule per second. You don't have, I mean, you don't have to write it down unless you really want to, but that's a watt. It's a joule per second. So, but what I'm going to do is I'm going to draw a black box. And what you're going to do is we're going to look at this black box and you're going to sort of guess what's happening. So I am going to take this black box, which is literally a black box, and into that, I'm going to put 1 joule of energy. What's going to happen to the black box? There's a couple of things that can happen.
Gonna heat up.
Yeah, it's going to heat up. We can store the 1 joule of energy inside it. Or what else can happen?
Could dissipate 1 joule of energy.
Or you can get 1 joule of energy coming out the other side. There's something very important here. It regards energy. What do we know about energy?
It can't be created, right?
Correct. Conservation of energy. And for the same reason, power is conserved as well, because it's just energy per unit time. So energy is conserved, power is conserved. It can neither be created nor destroyed. It only changes form. So if I put, let's say, 1 joule of energy into a black box, it has a couple of places that it can show up. It can come out the other side as the same form that it went in, or it can change form and turn into heat. 1 joule of energy coming out as heat. What if it was a noisemaker?
It'd be sound energy.
It'd be sound energy. What if it was a light emitting diode? What would it come out as?
Right.
But how much would come out? If I
1
put
joule of
1
energy.
joule in,
1 joule out.
1 joule has to come out. If I put it in at a rate of 1 watt, I can either use it to store energy, or if it's immediately converted into something, it had better be turned into 1 watt of something. Now, there's no saying that it has to be converted into just one thing. So let us say that I have a power supply that puts 200 watts of power, or 200 joules per second, into this black box. And this black box is called a radio. And in fact, we're going to say that this is a transmitter. Okay, a specific kind of black box. And we measure our output power going out to the antenna at 100 watts. Where's the rest of the power?
It could come out as sound.
To come out as sound? Hopefully not. But where else? I mean, it has to come out as something, right? Either it gets stored or it comes out as something.
So is it heat?
It comes out as heat. So has anybody ever seen a high-powered RF amplifier by chance? What does a high-powered RF amplifier have on it? How is it constructed?
Heat sinks.
Big heat sink. And sometimes it has a big fan that blows air over the tubes, or that heat sink, and takes the heat away, because heat tends to kill things, right? Heat is usually bad for things. So essentially now what you have is, if I have 100 watts out and 200 watts in, I could actually calculate an efficiency. Efficiency is power out divided by power in, which in this case is 100 divided by 200, which is 50%, or 0.5. So that would be a 50% efficient transmitter, which is actually pretty common. And that's also why your power supply is typically much bigger than you think it needs to be to run a particular piece of equipment, because nothing in the world is 100% efficient. Okay, so getting back to our discussion of Ohm's law and power and stuff, what we're going to look at is, we're going to have this circuit right here, and we're going to have power equals E times I, which is 12 times 12 is 144 watts. Now, we're also going to look at the resistor. How much current is going through that resistor? The way that this is drawn. If our current going into the resistor is 12 amps. Well, we don't have any branches in the circuit, right?
Right.
So it's not like we have any current, like if we were to draw it like this, we could have some current going this way and some current going this way, and they wouldn't be equal necessarily. But I didn't draw that. There's only one place for the current to go, and that is this way, through everything. So that's 12 amps. Okay, so now what we can do is say we have our resistance, we have our Ohm's law calculations. P is equal to E times I, or I times E. I'll draw it the right way. I'll be consistent. And the other one is E equals I times R. Well, so what we're going to do now is we're going to have this E equals I times R, and we're going to substitute it, because we know that power is equal to E times I. So now we have P is equal to I times R times I is equal to I squared times R is equal to 12 squared times 1 is equal to 144. Well, look at that. The power going in is the exact same as the power going out the resistor. We just showed that the power being supplied by the power supply is the same as the power coming out of the resistor. And what form does that power coming out of the resistor take? What does it look like?
Heat.
It gets hot. That's right. Okay. So here we go. Now, what we're going to do is say, if we were to rate this resistor and give it a power rating, what would our minimum power rating of that resistor be?
12.
It should be 144 watts. It's going to be measured in power. So now, what if this resistor was rated 1 ohm at 100 watts? What would happen to that resistor?
It would slowly burn up.
It would slowly burn up. And in some cases, it would actually happen quite quickly. I've done that myself, where you have a resistor that basically gets white hot and then turns into a pile of ash very, very quickly. So I have actually occasionally seen a short circuit put 100 something watts through a resistor that was rated at 1 ohm at 1 watt. What do you think happens to that resistor?
Wow, it would blow up. Well,
Again, it gets really hot really fast. I've seen one actually turn bright white and go a little puff of flame and then nothing left but char, black powder.
So
Okay,
how do we avoid that?
you try to avoid that. That actually has a name. That event actually has a name. Anyone know what the name is?
Destructo.
That's a potential name. We have another name. We call it
Letting the smoke out.
letting the smoke out. That's right. Because smoke is the magic stuff inside electronic components that makes it work. So all electronic components contain this stuff called smoke, right? As soon as you do something bad, it lets the smoke out. And since smoke is magic, the smoke is what causes it to work in the first place. If you let the smoke out, suddenly it doesn't work anymore. At least that's, that's the easiest way to think about it. So once you let the smoke out, it doesn't work anymore.
British car owners know all about that.
Are you saying something about Lucas Electric?
Dark prints.
Yeah. All right. So now what we're going to do next is take this resistor and we're going to add something to it. Magic smoke. Yes. We're going to add a second resistor and we're going to call this R1. We're going to call this R2. So now let's say that I am an electron. I'm very, very small. That's being generated by this battery, which has basically a storage of electrons. That's what a battery does. And I'm a particle that's floating around. Really, the electron goes this way. But again, we're going to imagine that's not the case. So let's say that I am something that is floating around inside this wire now. In order to get out of the battery and back to the battery, what do I have to pass through?
Both resistors.
Okay, these resistors are known as being in series because I cannot get through one and go back to the battery. I have to go through both of them. Just like if you're watching a series on television, you have to watch the first one and then you have to watch the second one. Right? So these resistors are in series. And the resistance that the battery sees when it looks out there is R1 plus R2, a simple calculation. They just add together. So if this is 3 ohms and this is 6 ohms, my total resistance would be
9 ohms.
9 ohms. Very good. Okay, now, importantly, how much current passes through both resistors? It's exactly the same.
Same.
It's exactly the same. All the current has to go through both resistors. All right, now let's say that this, instead of a resistor, was actually a resistive element in something that we call a light bulb. Does anyone have any experience with something like this? Anyone have a Christmas tree?
Christmas tree lights.
Those are Christmas tree lights. So what is the problem if you have something that burns out there?
They're all stop lighting.
They all turn off because you broke the chain. That's right. That's why we don't wire our houses that way. Instead, the way we wire our house does this. This is the way we wire a house, where we have resistance 1 and resistance 2. Okay, so now, once again, let us say that when we get, we're sitting in that wire, traveling along, we get to this point right here is called a node. That's a current node. We get to that point and we have a decision to make. Which way do we go? And how do we decide which way to go?
The path of least
Line
resistance.
of
The
least
path of-
resistance.
Path of least resistance, that's right. So if my total current splits apart and we have I2 and we have I1, they rejoin right here at this other current node, and they go back and they join back as current. Now, if this is, for instance, if R2 is really, really high resistance, we could actually draw it like this, which would be an open circuit. How much current would flow through that resistor?
Zero.
Nothing.
Zero.
That's right. All the current would go the other way. If we were to draw this again, and we made them exactly equal, how much current would flow each way?
Half of.
It would be half.
Same.
However, this is known as being in parallel because these two lines are parallel. The current can split, and both of the resistors experience the exact same voltage from the battery, which the more things you put on it, the more you require of the battery. Like I could add more parallel resistors here and more parallel resistors. This is how we wire our house. The reason we do this is because every device in the circuit experiences the exact same voltage from the power source, which means that even if this light, for instance, R2, burns out, the other lights will still be lit. And again, this is called wiring in parallel. So now, if I were to take this and redraw this and say that we had R1 and R2, and this is 3 ohms, and this is 6 ohms, they're obviously not equal, are they?
No.
Which one is going to have a bigger current going through it? Which is the path of least resistance?
3 ohms.
3 ohms, that's right. Now, what is the total resistance experience?
9
It's
ohms.
actually R1, R2 divided by R1 plus R2. You don't have to know this. For the general exam, you probably do. So it's actually 3 times 6 divided by 3 plus 6, which is 18 divided by 9, which is 2 ohms. So the battery will basically see that this is a 2 ohm resistance. And you could actually figure out what the total current is. And then once you know the total current, then you could also figure out what the current through each resistor is, and they should equal the total current. Okay, so that is practical applications of Ohm's law, series, and parallel circuits. And what we're going to do now is we're going to do other things. Okay, so the next thing we're going to do is ask this question. Can this resistor store any energy, or does it automatically instantaneously transfer something into heat?
It transfers. Doesn't store.
Okay, it transfers it into heat. Okay, so power that goes in is almost instantaneously converted into power that goes out. And for a resistor, does it care if a voltage looks like this or it's always just plus and minus the same way.
It doesn't matter.
This is AC, this is DC. Doesn't care. Resistor sees no difference whatsoever. Okay, resistors are boring. Resistors are really dull. What we're going to do now is we're going to draw this. And then we're going to draw this.
Capacitors.
Okay, this is a capacitor. And this is an inductor. Okay, so what makes a capacitor interesting? If I hook this up to a battery that has a plus and a minus, what will happen to the capacitor is that I will get a surplus of pluses over here and a surplus of minuses over here.
Isn't it more like a storage unit itself?
It can be used as a bunch of different things. That's one of the applications of it, but yes. So now let's take a look at the actual capacitor. So this is a capacitor. These are two metal plates, and inside, in between them, is a material that does not conduct electricity, called an insulator. That can be air, it can be plastic, it can be mica. Mica is a type of rock. It can be tantalum, it can be any number of different things, polyethylene. So now it can be ceramic, it can be paper. So now let's take a look at this capacitor. It's two metal plates. Well, let me fill this one with pluses and then fill this one with minuses. Ideally, what do pluses and minuses do?
Bring polarity.
Yeah, what happens if you have a plus particle? What happens if you have a plus particle and a minus particle? What do they tend to
They
do?
attract.
They attract each other. What happens if you have two minus particles, for instance?
Repel.
They repel. That's right. Okay. So what is happening inside this capacitor? I mean, what would happen if we didn't have those plates and they weren't separated by something? What would happen to those charges?
They would merge.
They would jump the gap. They would jump to meet each other. But we are doing something to physically hold them apart. And that is that we have built an environment where they can't jump. So they actually generate something called an electric field. And that electric field exists in between them. And it's measured in a voltage per distance, and it's dependent on the voltages that exist on those two plates. This is actually a storage unit. It's a storage mechanism for energy in an electric field. So now let's take this battery and disconnect it. What happens to those charges?
They remain there.
Do they have anywhere to go?
No.
They do not. They stay right there, don't
They
they?
stay right there. That's right. So we have now charged up a capacitor, stored energy in its electric field, and just left it there. So this can actually store energy in an electric field for a really long time until it sees something to discharge it.
So a battery is a capacitor then, right?
A battery is sort of like a capacitor. It's more chemical storage, but a capacitor can be used as a form of a battery. Not the other way around, but yeah.
Right, that's like those little boxes for jump starting your car, the capacitor then, huh?
Yep. Okay, so
Right.
now what we're going to do is take a look at this thing called an inductor. So this, again, a capacitor is an electric field energy storage device. Now, what we're going to do is have a current flowing through a piece of wire. Now, can everybody see that arrow with the eye? Okay, everybody hold up your right hand and stick out your thumb. This is an interactive exercise. Now take your fingers and roll them forward. If you have current moving this way, it generates a magnetic field in a loop around the wire, around the current. It can be in space, it can be through a wire. Basically, if you have a current flowing this way, you have a magnetic field flowing around it. which basically means that the same way that a capacitor, if you charge it up with a charge, will generate an electric field internally. If you run a current through a wire, you will get a magnetic field that exists around it. This is how an electromagnet works. Now, we can also be very creative about this and take our wire and form it in the shape of a coil, which instead of making those loops, will basically make a magnetic field that is now shaped like this. We'll have magnetic field lines that extend off in this direction with a North Pole. It's not necessarily on these ends, but a North Pole and a South Pole. And if you've used permanent magnets, that's the same thing. If you build an electromagnet, it's the same thing. If another version of this is known as a solenoid, can also be used as the basis for an electromagnetic switch, which is called a relay. So very, very useful. But now here's the next question. If we disconnect this power supply, which I'm going to draw. So let's say we have a power supply, which is a DC power supply, which is generating a current flowing through here, which is generating a magnetic field. What happens if we disconnect it?
The magnetic field will go away.
Well, not happily. What happens to the magnetic field? It's gonna go away, right?
Yeah.
But what happens to all the energy that's stored there? Because the magnetic field is storage, is a way of storing energy. What happens to the magnetic field? That energy exists.
Does it remain as a magnetic field?
Not really. I mean,
A
I've
new
never
magnetic field?
well, you have this magnetic field and it's got energy in it. The energy has to go somewhere, right? Well, sometimes what's a way to get rid of energy? You can burn it up.
Transmission?
You can burn it up in a resistor, right?
Heat.
Well, yeah, you could, it can be heat. You can also burn it up in a resistor that's temporarily connected, right? What happens if this resistor actually looks like this? What's the resistance right here?
Zero. I mean,
It's not
Infinite.
zero,
Infinite.
not
Infinite.
zero.
Infinite.
It's not infinite either. Air is not an infinite resistor. Let's say this has a resistance of 10,000 ohms. What will happen is that you will generate a voltage that goes higher and higher and higher until it generates enough voltage to say, okay, I just jumped the gap.
Dielectric breakdown.
That's,
Right.
yep. And basically this, does anybody have a car? This is how spark plugs work. You have a coil and then you break the coil and you give the high voltage that gets made because of the energy in the coil, you give it a place to jump. That right there is called a spark plug. It's a gap between two pieces of metal. The voltage gets higher and higher until it generates a spark and it ignites your gas. That's how an ignition system works. So capacitors and inductors can be a lot of fun. They're very, very useful. Now, the other thing about capacitors and inductors is that if I have a circuit that goes like this with an inductor and another one that goes like this, the job of an inductor is to generate a magnetic field. If I have a battery that is connected to two of them, how much magnetic field am I going to make? I'm going to make the sum of the two, but everything has to go through both of them, right? How about if I put them in parallel like this? Well, again, it's going to split the current. And so for an inductor, L1 and L2, these add. For inductors in parallel, L1 and L2, these actually go in parallel and they have That same funny looking equation. They basically, the calculations are very much like resistors. Now, capacitors are a little bit weird. So what I'm going to do first is draw this pair of capacitors. Would you say these capacitors are in parallel? Everybody, what do you think?
Yeah.
Okay,
Yes.
those capacitors are in parallel. Well, if
Yep.
this one has a capacitance of 3 farads and this one has a capacitance of 2 farads, could you see that they are actually plates like this? And instead of drawing it like this, I could actually just take those and make these plates bigger. Because these on the left-hand side all get charged up to plus at the same time. And these on the right-hand side are all minuses at the same time. Does everyone agree with that? So capacitors in parallel behave the other way. They actually add together. If you put them in series, it's the other equation. So this is the only weird one. Capacitors behave strangely compared to resistors and inductors. Okay, so now it's time to talk about AC, and we're going to take a break in just a couple minutes, okay? All right, so we're going to look at AC. This is AC, where our voltage, instead of just going on the top side or the bottom side, it goes from positive to negative. It has a period. And because it has a period, what does it also have?
Frequency.
A frequency. Okay, in the United States, we have a voltage. It's 120 volts. This is our wall voltage, VAC RMS. And we have a frequency of how many hertz?
60.
60 hertz, yes. How about if you live in Europe?
50 hertz.
50.
Yep, and what's the voltage?
220, 230, yeah.
230 volts, and frequency is 50 hertz. So that means it actually it's a bigger voltage, but it also takes longer to make one full cycle in Europe.
Less amps.
Yep, and less current. That's true. Okay, but since we're not in Europe, we're going to erase that. If you measure your wall voltage, you will actually see that it's 120 volts and its frequency is 60 hertz. Now, something that's interesting about our wall voltage is notice that it doesn't just say volts AC. What does it say?
RMS.
RMS.
Root
Okay.
mean squared.
Yes, root
Yeah.
mean squared. Okay. So I'm going to ask an important question here. If this right here is 120 volts, DC, and how do we know it's DC, that green line? Does it ever change? Nope, that means it's DC. It's always on the positive side. We have 120 volts. Okay, if I were to take this 120 volts and do my power calculations and say I have a resistor of 1 ohm, P is equal to, well, let's just say I have a, resistor of 1 ohm, and we'll do some Ohm's law calculations and say E equals I times R, and we have our 120 volts and 1 ohm. And we have E, I, R, like that. We don't know our current. I is equal to E divided by R is equal to 120 divided by 1 is 120 amps. Okay, so we have 120 amps and 120 volts. Well, okay, let's see the next thing that we can do with this. If we have 120 amps, and we have P, I, E. P is equal to I times E is equal to 120 times 120 is 14,400 watts. Okay, so that's with the DC power supply. But now I'm going to ask an important question to everybody. So you got to really think about this one. So if this is what our AC power looks like, we're looking at the black. When our voltage is 0, and our voltage is 0 here and here and here. When our voltage is 0, what is our power?
0.
We have no power.
No power at all.
That's right. So all those times we have no power. How about any time that our voltage is less than 120 volts? Do we have as much power as 120 volts would make?
No.
No. So in order to make up for that, what we have to do over a period of time that averages out is sometimes we actually have to go bigger than 120 volts. And it's actually also true because it's the square. It's the same thing on the negative side. So here's our less than 120.
And you're
And
talking about AC circuit, right?
We're talking about AC. So what we end up having is voltage that goes like this. And here's the 120 volt lines, plus and minus. And we have these peaks which have to go higher because in those times, we have to be able to account for the fact that we can't make as much power in all those other times, which are down here. Does everybody agree with that? When the voltage is lower than 120 volts, we can't make as much power because math says we can't. And when it goes through 0, we don't make anything at all. So the way to account for that is to go higher sometimes so that over a time period, over an average time, we make the same amount of power as a DC circuit would make. This is known as RMS, which is root mean squared.
And that's why I see 123 volts on my voltmeter when I stick it in the plug.
Actually, that's not. That's because you have fluctuation in your power supply.
Oh,
That can actually vary. If you were to measure this with an oscilloscope and get a graph of it, your peak would be 170 volts and your negative peak would be negative 170. It's actually 120 times the square root of 2. Because that is the equivalent peak voltage that AC has to be in order to generate the same amount of power as DC. So we call this voltage 120 volts RMS. That is your voltage. We call it 120 volts, but just important to know that when you actually go to measure it, if you stick your meter in the wall, it's measuring RMS voltage and not peak voltage. You actually have a peak that goes from plus 170 to negative 170. And if you're thinking about taking your general exam, this is on the general exam. All right, everybody ready for a 5-minute break? I know my butt is.
yep.
All right, see you in 5 minutes.
Yep.
Okay, everyone ready?
Yep.
Okay, here we go. So now, any questions before we go on? It's about to get more fun. Okay, so what we're going to do next is we're going to take a capacitor. Notice the intersection of capacitor and DC. So we're going to take a capacitor and we're going to hook it up to a DC power supply. Or a battery. So what will happen is the capacitor will charge up. Does everybody agree with that? And then nothing will happen because once it's full, how much more can you put in it? And the answer is nothing. Okay, what is current? Again, what's the definition of current, everyone?
Flow of electrons.
Flow of electrons. If our capacitor is now full, how much current will continue to flow?
None.
So let's say that your power supply didn't know what was connected on the backside of this magic wall. What would it assume was connected once the capacitor was charged up on the backside of this magic wall? If there's no current flowing at all, what would it look like? An open circuit. That's right. It would look like a big old nothing hooked up to it at all. So a capacitor for DC looks like it charges up and then it looks like an open circuit. Okay, so now let's hook up a capacitor to AC. Now, the interesting thing about AC is that AC goes through cycles. Half the time it looks like that. What happens when the voltage looks like that? This charges up to the plus, this charges up to the minus. But then what happens to the power supply? It flips. And now this is the plus and this is the minus. Well, what is already stored on that capacitor? You've got those red pluses and the red minuses, and what's going to happen?
It is going to reverse after.
It's going to reverse. Yeah. So basically you're going to get a flow of the pluses back to here and the minuses back to here. And eventually those will disappear and then you'll be neutral. And then you will charge back up, but now the other way. But then this thing will flip back the other way again, where this is now plus and this is now minus. And when that happens, what's going to happen? You're going to end up calling back all of these charges, just like that again. And then you'll go neutral. And then you're going to end up charging up the plates again this way. And now we've gone through one full cycle. So looking through the magic wall, what does the power supply see? Does the current ever not flow? Does the current ever not flow?
Constant.
It has to flow.
It flows. Okay. So if the battery doesn't know what's on the other side of this wall, and it says, well, the current always flows, what kind of thing allows current to always flow unimpeded?
Short circuit.
That would be a short circuit. So that looks like that. All right. So for AC, a capacitor looks like a short circuit. Now let's take a look at an inductor. An inductor is a piece of wire. For DC, what happens when current flows through a piece of wire? It's a piece of wire, right? Does it argue about it? No, it's a piece of wire. What is a piece of wire substituted by? A short circuit. Right? So for DC, an inductor looks like a piece of wire. Now, again, we're going to do the same thing over here. We're going to make this plus and this minus. So our current's going to go that way, and it's going to make a magnetic field that looks like this. But then we're going to switch it around, and the magnetic field energy is now going to have to go opposite. But the thing already had the magnetic field energy at the beginning, which says, no, wait a minute, I don't want to change. I already have magnetic field energy. And the easiest way to not have magnetic field energy to dissipate is to not allow it in the first place. Well, if it doesn't allow it in the first place, that means it didn't allow any current to flow. If it didn't allow any current to flow, what does this thing basically look like? If it didn't allow any current to flow, what does that mean that it looks like?
Open.
On open space.
An open circuit. So in the extreme, basically what we get is that a capacitor at DC and an inductor at AC both look like open circuits, and a capacitor at AC and an inductor at DC both look like short circuits. And those are, if we were to take this to the extreme, frequency equals 0 and frequency equals infinity. So the interesting thing about this is that for a lot of components, we can actually view it as this. For DC, if we want to allow current to flow, we use an inductor. If we want to block DC, we use a capacitor. For AC, if we want to allow current to flow, we use a capacitor. And if we want to block it, we use an inductor. But actually, as it turns out, we can actually take these, because not all frequencies are infinity and not all frequencies are 0. So if we have 0 is less than our frequency is less than infinity, that's when things get interesting, because a capacitor doesn't completely look like a short circuit, and an inductor doesn't completely look like an open circuit. They actually have another thing called Z, which is impedance. And that's measured in ohms, which is the resistance to flow of AC current.
Not gonna be up.
Go ahead. I thought I heard somebody have a question. No, okay. So these devices have reactance and impedance, and they are not equal to 0 and they're not equal to infinity. Now, if we draw an inductor and it's not perfect, does an inductor have a little bit of resistance as a piece of wire that isn't perfect? And the answer is yes.
Yeah, yes.
How about
Question?
yes, go ahead.
In your formula, 0 is less than F is less than infinity. F is frequency.
Is frequency. Yep.
Okay, thanks.
But what happens is that now, if we don't have a quite perfect capacitor, do we get a little bit of leakage of energy? Yeah, probably. If we have an inductor, do we get a little bit of heat building up? Yeah, a little bit. So they're not perfect, but they are, we're going to assume that they're perfect for this particular case. And as it turns out, they have these things called reactance. And that's also measured in ohms, just to be confusing, and impedance, which is also measured in ohms. And they also have this resistance. They also have a little bit of resistance, which oddly enough is also measured in ohms. Now, they have 3 things now that are measured in ohms, right? That's a little confusing, right? Everyone agree with that? I think it's a little confusing. Well, what it turns out is that these capacitor and inductor have kind of like a special thing about them, which is that, remember we drew a sine wave the other day? Heck, that was yesterday morning. Everybody remember yesterday morning when we drew a sine wave?
Yeah.
Yeah. Okay. And then we drew another one that looked like this.
In phase.
Does everybody remember that?
Mhm.
Okay, and we could look at the difference between the starting points of the two. And that was actually known as a phase difference.
Yeah.
Measured as like in degrees, because one full shift is 360 degrees. This would be a phase difference. That would be a phase shift. Well, as it turns out, capacitors and inductors, in addition to having impedance that depends on frequency, also generate something called a phase shift in a measured unit. So Ohm's law again is equal to what? Somebody give me Ohm's law.
IR, equal to IR.
E equals I times R. But what are we actually working with now?
Let's see.
We're working with Z. So for capacitors and inductors, we could actually write E is equal to I times Z. And the way that capacitors and inductors work is that an inductor actually causes a phase shift, and a capacitor also causes a phase shift. So the easiest way to draw this is we're going to make our circle again. And this is our 0 degrees. Resistance always lies on that axis. That's our resistance. However, our reactance, and thus what our capacitor and inductors do, inductance goes up. And our capacitance goes down. On this circle. So if we were to say that our resistance was 4 ohms and our capacitance was measured at 3 and our inductance had a reactance of 3 ohms and it was perpendicular, what is the length of that vector?
Sine of 45.
Well, no, it's not. It's a 3, 4, 5 triangle. Everybody remember the 3, 4, 5 Pythagorean triangle?
Ugh.
Uh-oh. This would be 5 ohms. If we were to measure the impedance, we would find that it was 5 ohms, even though we had a 4 and a 3 going into it. We would have an impedance of 5 ohms. And interestingly, our impedance would actually not be, our impedance would actually have an angle. Yes, that's right. A squared plus B squared equals C squared. And in fact, what would happen is it would be 5 ohms with an angle. And this is about 37 degrees. And because it's going this way on the circle, it's going in the positive direction. So we would actually have an impedance of 5 ohms with an angle of 37 degrees. So now if we go back to our E equals I times R and replace it with Z, we would actually end up with that angle of 37 degrees. And what that would mean is that our voltage would actually be shifted 37 degrees ahead of our current. And we would actually be able to see something like this happen if we measured them. If we had a capacitor, instead, it would actually go the other way. It would be down here. It would still be measured at 5 ohms, but the angle now would be negative 37 degrees. And instead, we would actually find another graph that looked like this, which would be shifted the other way. It would be delayed by 37 degrees.
On your sine diagram with the phase shift, where are you measuring the 37 degrees?
Oh, it's this triangle right here.
I was talking about the sine wave diagram in the middle of the.
Oh, yeah, because one full cycle is 360 degrees. So
Where's
if
the
it's,
37-degree mark?
well, it would be about here or there. I was approximating. It's about 1/10 of a wave.
Okay, so it's 37 over 360 in
Right,
the unit measured, right?
right.
Okay.
And what is important here is, let's say that you wanted to cancel out something that went up. An inductor causes it to go up. You have that imaginary impedance. What would you use to cancel out an inductor?
Capacitor?
A capacitor. What would you use to cancel out a capacitor?
An inductor.
An inductor. Yeah, isn't that funky? They operate opposite each other. Okay, this is actually really important because, as it turns out,
Does
what
an inductor
happens-
have a different name?
no. Impedance is impedance. One generates a positive shift, the other one generates a negative shift. So as it turns out, we're going to have an impedance of an inductor is 2 pi FL, where F is the frequency and L is the inductance. So what do you notice about that F? What is F?
Frequency.
Frequency, yeah. So what that means is that the impedance changes with frequency. And for a capacitor, Z is equal to -1/2 pi FC. So as you can probably see, when the frequency goes up with an inductor, the inductance goes up. When the frequency goes down on a capacitor, or the frequency goes up on a capacitor, the impedance goes down because the denominator gets bigger. So let's say you want to have these completely cancel each other. You set them equal to each other and you end up solving for frequency, and frequency is equal to 1/2 pi square root of LC.
And what is L in your
L
first
is the
equation?
inductor and C is the capacitor.
Gotcha.
This is known as resonance. That's known as resonance, and it is the point at which they completely cancel each other out. And why is this important? Why is resonance important? Okay, resonance is important because of the following. Let us say that we have this circuit. Okay, this is a really simple circuit. Everyone agree with that? Very, very simple.
Yeah.
Okay. At the point where these cancel each other out, we have ZC is equal to ZL, except that this one is negative and this one is positive. So at that particular point, these are equal. And what is minus and plus when you add them together?
0.
0. And what happens when you get a 0? What does it make these things do? Looks like a short circuit. And if you go off of that particular frequency where that's true, what happens to the impedance? It tends to go up. So if we were to draw a frequency response chart, so this is amount of energy allowed to pass versus the frequency, and we go from 0 to infinity, we would find at our resonant frequency We're way up here. As soon as we move away from it, it drops off. As soon as we move away from this, it drops off. What is that thing called where it allows just a certain number of frequencies to go through?
Looks like you built a filter.
That is a basic filter. We can also use this to generate frequencies. If we use it to generate frequencies, in particular, one frequency at resonance, we call that an oscillator. So a simple circuit that contains an inductor and a capacitor is the basis for every frequency dependent thing that we will ever do. That's why I say resistors are really boring and capacitors and inductors are super, super important, because we can use them to block frequencies, we can use them to pass frequencies, and we can use them in conjunction to build filters and oscillators. And if we're trying to make a radio frequency, we're trying to generate a frequency. How do we generate a frequency? We use an oscillator. If we're trying to build a mixer which combines two frequencies, we have stuff coming in off of an antenna and stuff that, and a frequency we want to combine it with. How do we make that frequency?
Filter
We use an oscillator.
it.
Okay, so what happens if we have this? So we make that a variable capacitor where we can change our capacitance. We can actually change the value of C. If we can change the value of C, what happens to the F?
Goes up.
It goes up or down.
Down.
On the
It
scale,
goes up or down.
Right.
What basically means if we now have a tunable variable capacitor, what can we do to our frequency?
Modulate it.
We can tune it. Yeah. So now we have a tunable oscillator or a tunable filter. We can also have an inductor that we can vary. So we have even more flexibility. And by doing that, we would just build it accordingly. We could switch a different one in and we completely change the resonant frequency of the circuit. We make it behave totally differently. So how's that for fun?
I know I'm
I
thrilled.
mean, it's all.
All right, somebody asked the question.
it's fun if I'm gonna build a radio from scratch.
That's right. But now here's the question. What does an amateur license allow you to do? You just said it.
Operate on different frequencies.
No, you actually
Yeah.
just said it.
You can make
Radio from scratch.
radios.
You can build a radio from scratch. In addition to that, you are legally allowed, you put it on the air. So that's why we're required to know at least something about this, because you can make your own radio, you can make your own antenna. You do, okay, let's say that you go and you buy a radio and you buy a business band radio. Let's just hold this one up. This isn't a business band radio, but let's say this is a business band radio or an FRS radio. Those radios have to be constructed per requirements laid down in either part 90 of the FCC rules or part 95 of the FCC rules. These are very, very restrictive that tell you exactly how it has to be built, and they have to be tested in the factory for spectral purity, and they have to get an FCC stamp in order to be allowed to be used. Amateur radio, does everybody remember the part number that we follow?
97.
Part 97. That is the part of the FCC rules that governs amateur radio. There are specifications that say that all spurious emissions coming out of a transmitter have to be at least a certain number of decibels below the fundamental frequency, for instance. And it has to have a maximum power output, et cetera, or, there's a maximum power output that you're allowed. And other than that, there are no rules, which means you can buy something that's been built to that. You can design something yourself that's been that will meet those specifications. You can build it and you can self-certify that it works and be okay doing it on the air. You're basically allowed to sidestep all of those rules that govern how other equipment is built and constructed and used by virtue of the fact that you have an amateur license. You can't use your equipment in those same bands that the other ones use. But if you want to build your own stuff and experiment with it and try new techniques, you are absolutely allowed to do so as covered in Part 97. And that's why that's why it's necessary to learn this kind of thing. Because as I like to say, you know, it's like if you go and you get a license to drive a car, you don't necessarily have a license to build your own car, but you can drive any car that is acceptable to drive. It doesn't say you're only allowed to drive one type of car. We're actually allowed to go even further. There's no age requirement. You can be 7 years old and get your amateur license and build a piece of equipment that puts out a kilowatt and be assumed to be doing it legally where you don't cause interference to anyone. This is, you know, it's the kind of like the ultimate RF experimenter's box. So even if you only plan to use it for a little bit, that's why you have to go further.
No, there's 3 levels of licensing, correct?
Yeah, but any level of license can do this. Basically, any amateur license is allowed, you're allowed to build your own stuff. You have to stay within the specifications of the license that you're getting, but you're always allowed to build your own stuff. That is conveyed by the amateur license, the amateur service in the first place. And yes, you can build your own drone so long as it meets the FAA requirements. You can do all the communication stuff for, you know, for a drone. You can do all the communication stuff for a satellite. Okay, so let's see, who was it that's building a satellite?
Yo.
Speak up, Cass. Let's hear about the comm stuff on your satellite.
Oh man. Okay, so here's the thing. I've mostly been doing the structural stuff on it. Right now, for our most recent satellite that we put up into orbit, I believe it uses like L-band and VHF.
Okay.
Amateur bands, and then the next satellite that we're putting up is an L-band and a U, I believe.
And the thing is, you guys are allowed to self-certify because it's an amateur satellite. You don't have to go and buy something from Qualcomm.
Yeah.
You can build it yourself, and typically you basically buy components and put them together.
Yeah,
make 'em
commercial
work.
stuff is definitely what we're trying to aim for, things that are accessible to nearly everyone.
Right, but you don't have to like take your entire communication system and get it certified.
No, not at all.
Right, because it's an amateur system.
In fact, we have 4 frames that are letters from like Thailand and Russia saying that they're kind of mad about the amateur frequencies that we're using and they are asking us to stop. And we said, no.
No, you're legally allowed. So,
Yep.
yeah. Okay. All right. So let's see, back to, okay. So now we're going to jump over to some schematics, and actually we're going to do numbers first. We're going to do numbers and then we're going to do schematics. And some other devices and things like that. Okay. So let's do quickly some powers of 10. Okay. And then we'll get back to schematics. So powers of 10. 10 is a great number because it implies a 0. So if we do, for instance, 10 times 10, that's equal to 100. We can write this as 10 to the first power and 10 to the first power. And we get 10 times 10 is 100, which is 10 to the second power. So the bottom part is the base. The upper part is the exponent. If the bases are the same, all we have to do is add the exponents. So we can do 10 to the fourth power times 10 to the ninth power and know very quickly that it's 10 to the 13th power. We can also use this to our benefit by dealing with very, very small numbers. We can have 1/10 is equal to 10 to the minus 1 power. We can also have 1 is equal to 10 to the 0 power. Right? So this is basically how we represent powers of 10. So we can actually say that 1 over 1000 is 10 to the minus 3. We can multiply this by 10 to the minus 6 and get 10 to the minus 9. We can then multiply that if we want by 10 to the minus 9 and get 10 to the 0, which is 1. So what it means is we don't have to deal with all those, pesky decimal places, because if we could write it out, we could do 0.00001 times 0.000, and we get times 0.000000001 times a billion is equal to 1. I think we all prefer to work in this realm. That's a lot cleaner on the page. This is scientific notation. This is using exponents. Now, these things also have names. So we can write 10 to the 12th power, 10 to the 9th, 10 to the 6th, 10 to the 3rd. We can have 10 to the minus 3rd, 10 to the minus 6th, 10 to the minus 9th, and 10 to the minus 12th. Because we already know, for instance, that there are some things that are really big, like frequencies. This is mega, which is big letter M. 10 to the 3rd is kilo, like a kilogram or kilohertz. That's 10 to the 3rd power. And 10 to the 9th, we work in gigahertz all the time. And if you have a large computer hard drive, you have a terabyte hard drive, which is a billion. Sorry, which is a trillion. And then we can go smaller. This is a millimeter, little letter M. This is a micro. That's a little letter mu, which is Greek. And then we have nano, like nanobots, which is a little letter N. And then this is pico, which is little letter P. Well, it turns out that like a 1 Henry inductor is huge, and a 1 farad capacitor is enormous. So we typically don't deal in things like that. We deal with capacitors that are like 100 picofarads or 1 millihenry. And because of that, we end up with something that operates in megahertz. Let's say 72 megahertz. So we're dealing with a lot of really big numbers, and being able to use these prefixes like pico and milli and mega really, really comes in handy. So it's important to know those. It's important to be able to convert them. To know, for instance, at 0.00001 farads, well, we're going to move the decimal point. 1, 2, 3, 4, 5, 6. So that's the same thing as 1 times 0.00001 farads. We can write that as 1 times 10 to the minus 6 farads, and we know that 10 to the minus 6 is micro. That's 1 microfarad. Yes. Somebody said something there. Nope. Okay. So we can also say that, okay, we have 0.00006 Henrys. We can take this and we can do 1, 2, 3, 4, 5, 6. We'll put a 0 there. And we have 60 times 10 to the minus 6th, which is 60 microhenries. This is micro. So it makes it a lot easier to write these things down and use them in, well, for instance, lots of other different formulas, like F is equal to 1 over 2 pi square root of LC. Those L and C are usually going to be really small. Well, actually, if those are really small, our F is going to be really big. So if these are in the micro and nano and pico range, this is going to be in the megahertz and gigahertz range. So it's very useful to have those numbers available to us and have those prefixes available. The other thing we use them for is we use them for this thing called a decibel. Anyone ever heard of a decibel? If you do
Yes.
audio, you've done decibels. Okay, so a decibel, or in specific, a bell, is a measure of one thing compared to another. It's a measure of a ratio. So for instance, if I have 10 watts compared to 1 watt, we could say that is 10 times bigger. If I have 100 watts compared to 1 watt, we could say that's 100 times bigger. If I have 1,000,000,000 times, we could say that is 1,000,000,000 times bigger. But those numbers can get really, really big. It's a lot. It's kind of a pain in the neck to carry all those zeros. So a long time ago, it was determined that a bell was going to be equal to the logarithm base 10 of P2 over P1. Okay, so a logarithm base 10 is basically the opposite of 10 to the something is equal to something. So this is basically saying, what power would I have to raise 10 to get the result? So if I wanted to take, let's say 100, let's say 1,000, to what power would I have to raise 10 to get 1,000?
1/3.
10 to the third power, because 10 to the third power is 1,000. That means that the log base 10 of 1,000 is 3. That number is the answer. So if I were to write this down and compare something that was 1,000 to something that was 1, I would get the log base 10 of 1,000 divided by 1 is the log base 10 of 1,000, which is 3. That would be 3 bells. And yes, it's named after Alexander Graham Bell. Well, it turns out that that number really wasn't big enough. So they used something called a deci, D-E-C-I, which literally means 1/10, and created something called a decibel, which basically means that they had to take this and multiply it by a factor of 10 to get something that was 10 times bigger. They had to multiply it by 10 all the way through, and then that became 30 decibels. So the end result of this is that if something is 10 times bigger than something else, it is 10 dB larger. If something is 20 times bigger than something else, well, that how would you make up 20? It's 2 times 10. Well, okay. Before we do that, let's do 100 times. And that's 10 times 10. So every time we go up by a factor of 10, we have 10 decibels. So if something is 10 times bigger, it's 10 decibels bigger. If something is 10 times bigger than that, it's another 10 times bigger. So that's another 10 decibels, and we add them together because we're adding exponents. So we have a gain of 20 decibels. If we have something that's 20 times, we have 2 times and 10 times. Well, the 10 times we already know that's defined as 10 decibels, but then we have this funky 2. And it turns out that the logarithm of 2 is about equal to 3. Not exactly, but it's pretty close. So for engineering use, we use the value of 3. So we have 3 dB plus 10 dB is 13 dB. Okay, so now the obvious question that you're going to ask is, why do we do this at all? Well, what this allows us to do is represent really, really big numbers and really, really small numbers. For instance, if I have a transmitter that puts out power on this end of a long path, and there's another station over here that has an antenna, And this puts out 1 watt. By the time it gets here, at the other end, this much power is there. All right, what do you do with that? What do you do with it? How do you figure out, okay, how do you represent, practically speaking, how much of the energy is still there? What is the loss? What is the difference between the two? Well, using decibels, we can do that. 10 log base 10 of 0.00000000001 divided by the original. And that's 10 log base 10 of 0.00000000001. And we can count our decimal points. Go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we move 12 points. So that would be 10 times minus 12 minus 120 dB. And that is the power of doing this. Because now let's say that we're going to replace an antenna. Antenna gain is measured in decibels. This has a gain of 8 dB. And this one has a gain of 6 dB. All right, so we had a path loss of minus 120 dB in here because that's what we figured out. So if we have 1 watt down here now, and we go up 8 and down 120 and then up 6, how much do we get at the other end? Well, we have plus 8 minus 120 and plus 6 is minus 104. No, that's not right. Minus 106. So that is our overall path loss. And we can figure out if we have 1 watt here, exactly how much energy gets to the other end. And did we need to carry any weird decimal points at all? Did we have to factor in all those decimal points? And the answer is no, they're all contained in this number right there. So as far as what you need to remember with regard to decibels, there's really only 2 things. If I go up by a factor of 10, that's plus 10 dB. If I go down by a factor of 10, that is minus 10 dB. If I go up by a factor of 2, that is about 3 dB. And if I go down by a factor of 2, that is about minus 3 dB. And the nice thing is that almost anything you can find, you can do this the exact same way. So let's say that I started at a power of 6 watts and I ended up at 130 watts. All right, we're not going to get an exact answer, but what's the ratio of 130 divided by 6?
About 20.
Yeah, it's about 22. All right, so it's about 22 times. So that's about, let's try 3 times. Nah, we're not going to do that one. It'll be doubles. So it's about 2 times 10. So every time we go up by a factor of 2, that's 3 dB. We go up by a factor of 10, that's 10 dB. Then, if we did it again, we'd get 40. We doubled it again. So it's not that big. Maybe it's 13.5 dB. So that's close enough. We could say that it's just 13 and probably be very, very, very close. So I can grab my calculator and let's see, 130 divided by 6. And I can do a log base 10 and multiply by 10. And look at that. I get 13.36. As they say, close enough for government work. right? That would be an engineering approximation. And did I have to do anything other than multiplying by 2s and multiplying by 10s? And the answer is no. So like I could, when does class end? It ends at noon. So for instance, I could go and say, okay, I want to start at 3 and go up to 725. All right, well, let's just use 2s and 10s to see how to get there. So we go from 3 to 6 to 12. Let's see, 24. Yeah, let's go 10. I don't really like that one. So let's go to 3 to 6 to 60 to 600. Ooh, that's a good one. That's pretty close. So that's 2 times, and that's 10, and that's another 10. So that's 3 dB plus 10 plus 10, and that gets us to 600. And so let's say it's 23 dB. Go back to the calculator and see if we were even close. 725 divided by 3 log times 10. I get 23.8. So close enough for a rough order of magnitude. And that's all you really need to know. When you go through the math on the exam, there's only a couple of questions that could get asked. If you remember this, you'll never have a problem with it. To be honest, I never go any further than just doing this on my, and I'm all the way through the extra, and I work as an engineer. If I'm looking at approximate gains, this is how I do it.
Scott, what was on that bottom when you went from 3, 6, 60, 600?
Oh,
What were you showing us?
yeah, I'm finding a way to go from, let's say, 3 up to 725 just by factors of 2 and 10. Because those are the things that I know by heart.
Are those watts or decibels?
No, neither. These are in watts. Let's say I want to go, let's say I go from 3 up to 725. How would I get close to 725 starting at 3, just multiplying by 2s or 10s? So let's try another one. Let's go from 2 watts up to 968. All right, so we go 2 and then multiply by 2 to get 4 and multiply by 4 to get 8. Okay. And multiply by 10 to get 80 and multiply by 10 again to get 800. That gets us pretty close to 968, because if we went up again by 2, we'd get to 1600. So we're closer to 968. So that's 2 times, 2 times, 10 times, 10 times. Well, okay, 2 times is 3 dB, 2 times is 3 dB, 10 times is 10 dB, 10 times is 10 dB, and we get about 26 dB. And then maybe another one for good measure. We'll just call it 27, just for the heck of it. And now if we go back to the calculator, we'll take 968 divided by 2, take the logarithm, times 10, and we get 26.8. Close enough. And a heck of a lot easier than multiplying by decimal points and all that other stuff.
So what's the goal here? The goal is to determine the gain in decibels?
Yep. Because the main reason for this is, let's say you buy an amplifier, or you're going to specify an amplifier to purchase. An amplifier will typically not be specified in watts. It will be specified in dB gain. An antenna that you build or buy or whatever, let's say that it looks like this. If you work in a sensors lab or something, and this is specified with a forward gain of 12 dB and a front to back ratio of 32 dB and a front to side ratio of 40 dB. This means that somebody used a plot and they actually took a circle and they found that if this is the 0 dB line, the pattern would look like this. And it would max out at 12 dB. And in the back direction, it would look like this. It would have a little bit of power going backwards and more power going forward. And then you could also from this figure out your 3 dB beam width, as it's called. And what is 3 dB equal to again? How much power?
An increase like a double.
Or down, or 3 dB lower, that would be negative 3 dB.
Oh,
So
I see.
this is known as your 3 dB beam width, where your power is down 3 dB from the peak. This is also how we measure filter performance. If we have a filter that the passband of a filter looks like this is measured in, let's say this is our 0 dB point. This is our minus 3 dB point here and here. This is known as, this is the 3 dB bandwidth. So decibels show up everywhere. We also can have something called rejection, and that could be measured as, let's say, 60 decibels. That would be our rejection. The other one is that shows up is that, let's say we're building a transmitter, and our transmitter, here's our output measured on our spectrum scope, and here's our frequency, and here's our fundamental, which is what we're trying to put out. And this is on a logarithmic graph. And we see, because no transmitters are perfect, that we end up with these little harmonics and spurious emissions at different points. There are specifications that say that the maximum harmonic or spurious emission outside of the fundamental must be at least, let's say, minus 50 decibels lower than the fundamental. Those are in the FCC rules. When we go to build stuff, actually, when you go to buy stuff too, that says how big those have to be. And it doesn't specify what that power output is. It just specifies that whatever this is, this right here has to be at least, let's say, 50 dB lower. That translates to 0.00001 of whatever this level happens to be. And that's why we need to know decibels. Decibels are really important.
That's an antenna or amplifier calculation?
Amplifiers are calculated in decibels, you know, antenna gain, amplifier gain, preamplifier gain, path loss, gain, cable loss. If you have, let's say, 100 feet of cable that goes from end to end, its loss is going to be specified as 3 dB per 100 feet, or 2 dB per 100 feet, or really good cable, 0.6 dB per 100 feet. And it's going to be frequency dependent as well. The higher the frequency, the worse the loss becomes. The smaller the cable, the worse the loss becomes. So for instance, I could go to, let's see, cable loss chart. Here we go. Just going to go on the internet and find a cable loss chart. Coax attenuation chart. And notice how it's measured. Yeah. What are the units? Decibels per 100 feet. And it's measured by frequency on the left-hand side and by the type of cable up across the top. And the grid gives you what the loss is per 100 feet. So if you run a really short piece of cable, you won't have much loss. If you run at low frequency, you won't have much loss. If you run really fat cable, you won't have much loss. If you run a really long piece of cable, your losses go up, and when you get longer, your losses go up. And when the cable gets narrower and narrower, like RG174 is about 1/8 of an inch across. It's really, really low loss. I mean, really high loss, you don't want to use it for anything more than a couple of feet at a time.
So if there was a problem on the technician level quiz, that was, what is the decibel change from 10 to 20 watts? That's
Three-
still 3 decibels.
That'd
because
be
it's
3
double.
decibels.
It
Yep.
doesn't matter the number that you start off with
Because it's a ratio.
logarithmic
Because it's a
scale.
ratio,
right?
because it's a ratio.
I see. Okay.
If
Thank
you go from 10 to 20, that's the same as going from 100 to 200. It's the same as going from 1 million to 2 million. If you,
That's pretty incredible to think about. Thank you.
Yeah. all right, other questions before we get into schematics and some other components. Is this making sense to everybody? There's a lot to learn, I know, but that's why, okay, but that's why it's important to go through and be practicing, be practicing on the exams and stuff like that. Well, it's amazing to realize just how much power is needed to increase decibels. Yes and no. What if you're running a milliwatt?
Well, that's true. Then the decibels would not be so difficult to
Right.
grow.
What's important to note is that let's say that you're running a 5-watt transmitter compared to a 500-watt transmitter. Right? How many decibels is that? So let's say you go from 5 up to 500. Okay, that's 10 times 10 is 100 times, is 20 decibels. Okay, by convention, if you look at a radio, 1 S unit, as it's called, is about 6 decibels. So by switching from 5 to 500 watts, if you were originally an S6, you would now be an S9. If you were an S0, you would be an S3. There are times when using extra power is really useful. There are times when it really doesn't matter. You'll find that it really doesn't matter. But here's the really important question. How much power do you need to put into an amplifier to produce 5 watts? That would be about 10 watts. How much power do you need to put in an amplifier to produce 500 watts? That would be about 1,000 watts. So essentially, if you are running off of a battery, right? Which is easier to produce, 5 watts or 500 watts?
500 watts.
Well, no, off a small battery.
Oh, small battery. Yeah, just 5 watts. Yes.
5 watts. And because the losses go up a lot, you're generating a lot more heat. At some point, I mean, let's say you're running a 1,000-watt amplifier. There are a lot of 1,000-watt amplifiers that you can't even run off of a 120-volt circuit. You need a 230-volt circuit. You basically need dryer power.
That's true, and that's the volts that they use in Europe, like you mentioned earlier.
Right, but if you're using that in the States, you actually need to pull a dryer circuit into your station to run a big amplifier.
Oh, I see. That's good to know. Thank you.
And that's why a lot of people, they say, okay, the most I'm going to run is about 500 watts, because above that, I would actually need like additional circuitry. I'd need a separate power drop out of my breaker box.
Sure.
So, I mean, when it comes down to it, we're talking actual power. We're talking power that you have to source from somewhere. And, you can only pull about 1,800 watts out of a 120-volt circuit. So if you want to output 1,200 watts, you need a dryer circuit. Dryer circuit can put out what, about 4,500 watts, I think, roughly. So, but you need to run a separate power drop.
Thank you.
Okay. Yep. A lot of practical stuff in here, isn't there? Okay. So what we're going to talk about now are, let's see, we're going to do batteries, and we're going to do, so if anyone's curious, we are going to go to page electronic circuits and components and circuits in the book. It's on the 23rd page of the PDF. I don't know if it has page numbers, what it would be. Maybe somebody will chime in for that. But the page looks like this. Okay, so that's what the page looks like. So a type of component often used as an adjustable volume control. It's a variable resistor that's known as a potentiometer or a pot. It's used to control resistance. It changes resistance with a knob. We've already covered capacitors and inductors ad nauseum. Batteries. Okay, so there are multiple different kinds of batteries out there. Your classic battery, like an alkaline or a carbon zinc battery, is not rechargeable. It is a single use. Now, there are also lithium metal batteries that are single use and not rechargeable. So the ones that are rechargeable would be like a NiCad, nickel cadmium, or a nickel metal hydride, or a lead acid battery, which is what you have in your car, or a gel cell, which is a gelled electrolyte lead acid, or a lithium ion battery. I also have a lithium iron phosphate battery that's rechargeable. So your carbon zinc batteries, those actually used to be called heavy duty. They were anything but. So those are not rechargeable. The ones that are rechargeable, again, lead acid, lithium ion, which is what you have in your devices, you know, portable devices in electric cars. Those are lithium ion. All right, now we're into diodes. Okay, now what we've covered so far are things that are just basically pieces of wire and made of metal, right? We have a resistor. That's usually a piece of carbon. It could be also a piece of metal. We also have a capacitor that's two pieces of metal separated by a space. And we have this inductor, which is basically a coil of wire. Well, now we're going to introduce something else. We're going to introduce element Si and element Ge, which are silicon and germanium. These are known as semiconductors. Yes.
What page? What page are we on?
It's the one that's labeled as, oh heck, I lost the page. It's labeled as
I have
diode.
26, but others have had 24.
I have it as
24, yeah,
20.
24.
I have it as the 27th page of the electronic PDF. And it's called, it starts diodes.
Page 24 on the what's labeled on the pages.
Okay, thank you. Okay, so these are semiconductors, which basically means they're not insulators and they're not good conductors. They're sort of in between. And if you look at how silicon exists, it's element number 14. It puts it squarely in between two noble elements, or between neon and argon. Its electron shell, its outer shell, has a maximum of eight spaces. And of those 8 spaces, it's got 4. So it's literally halfway in between. There is germanium, but we're not going to deal with germanium today. We're just going to deal with silicon. So basically, silicon is sort of, it's not really a conductor, but it's not really an insulator either. It's in between. However, what's cool about silicon is that we can actually take silicon and we can inject, as we're making it, a little bit of boron or phosphorus or arsenic or any number of different things that have a couple of extra electrons, or they are lacking a few electrons. And by doing that, we can give it a few extra electrons. And if it has extra electrons, it becomes slightly negative because electrons are negative. We could also throw some stuff in there that has a few extra what's called holes. A hole is a missing electron, and that would give it a slightly positive charge. So we have 2 different types of silicon. We have, well, really 3. We have the intrinsic, which is just plain old silicon. And then we have these other things which are called doped silicon, which have a couple of impurities in them that make them they lean one way or the other. By adding that doping component in between, what we can do is we can make it so that it tends to direct current in one direction and not the other. So what we can do is we can then take our P and our N, for instance, and we can stick them together. And we have a PN junction in our silicon, and this makes something called a diode. And a diode is a very special thing. It has an anode and a cathode. This is drawn like this. Notice it looks like a one-way sign on a street. This is the anode, and this is the cathode. And when we hook up a diode usually looks like this, like a little tube, and it has a band on the cathode end, which is the negative end. Easy to remember because the negative sign looks like that. What's special about a diode is that if I put a voltage here, a plus over here, and a negative over here, this will allow current, because it's like a one-way street, to flow through the diode. If, however, I reverse this and make it so the diode is now connected like this, well, it would, in theory, go this way. But which way is the one-way street sign pointing? To the right, which basically means that this is not a path that it can take. So a diode is a very, very important device for this reason, because it allows us to conduct current and energy in one direction and not the other. Now, why this is important? Because let's say that we have a signal that looks like this. What is this thing called again?
Sine wave.
A sine wave, and this is what we have for AC, right? And when we have AC, we are positive and we are negative. So let's say that we have this AC power supply, which is our wall voltage, and we run this through a diode. Well, it flips back and forth, right? And I'll put a resistor over there so we don't blow up the diode. It flips back and forth. So some of the time it's plus, and when it's plus, we go plus and minus, and we have current flow. And then sometimes it flips back the other way, because that's what AC does. And then all of a sudden our diode is reverse biased, as it's called. So the plus is here and the minus is here. And what happens then? It looks like an open circuit, which basically means it only conducts one way. And it only conducts for half of the time whenever the voltage goes in the right direction, which basically means that this voltage that we are putting in, when it comes out, this stuff on the bottom is now gone. Over here, what we end up with is something that looks like this, which is just the tops. Well, if it is plus, does it ever go minus? It goes to zero, but does it ever go to the minus?
No.
No. If something only goes in one way, what do we call that?
Directional.
If voltage only goes in one direction, what do we call it?
DC.
DC. What have we just done? We've converted AC to DC. This is known as a rectifier. And now what we're going to do is we're going to take this, and now that we have this humpy looking DC, we're going to take this and we're going to run this through a capacitor, so that whenever the voltage builds up, it charges up the capacitor. And whenever the voltage drops off, because the diode doesn't want to conduct, the capacitor then takes over the job And instead now our voltage looks like this.
Does that happen at the speed of light?
No, it's not quite at the speed of light, because what is the frequency of wall voltage?
Oh, 60 hertz.
60 hertz. So it's happening at about 60 hertz. And actually, what ends up happening here is that you end up with this, instead of camel humps, you end up with this, what I would call ripply looking DC voltage. And then you would take this and you would put this through a resistor and then a special kind of diode called a Zener diode, like that. And a Zener diode is a special diode that works backwards. And when the voltage gets up to a certain point, it says, nope, that's my maximum. So let's say this is right here. This is a line that says, 5 volts. And this Zener diode is rated at, let's say, 5 volts. It basically says if there's anything higher than 5 volts, I'm just going to turn on and dump it to ground. So the end result of what comes out of this power supply, it looks like that. And what does that look like?
DC.
That is nice, smooth DC, which is exactly what comes out of your power supply that charges your phone, or that is on your USB signal. USB, I believe, is 5 volts. So this is a very basic power supply. And what we've done is we've converted AC into DC. Now, the other thing that we need to do here is that it is very difficult to, let's say, and kind of wasteful to convert 120 volts AC into 5 volts DC directly. I mean, that's basically kind of stupid and we would never do it. What we would do instead is we would do something like this. Anyone know what this thing is called?
Transformer.
That is a transformer. Okay. A transformer is a pair of inductors wound around a common coil that constrains the magnetic field that's generated, so that you end up with a magnetic loop that's generated by one coil and picked up by the other coil. So if a current makes a magnetic field makes a current. Very convenient and actually very, very efficient. And what's cool about this is that the number of turns around the coil is proportional to the voltage that's generated. Robots in disguise, by the way, Drew. So this is N1, and this is N2, and this is voltage 1, and this is voltage 2. So the number of turns is the N ratio, and that's actually proportional to, the voltages. So if I have 120 volts here and I want, let's say, 12 volts AC, and this only works with AC, not DC, then I would have a ratio of 10 to 1. That would be my turns ratio on my transformer to convert from 120 volts AC to 12 volts AC. Now, interestingly, if I were to do that, and let's say I hook this up through a resistor that is a 1 ohm resistor, I could figure out what my current is. And I could say E equals I times R. And that's 12 is equal to I times 1. I is 12 amps. Okay, so what is my power? P equals I times E is 12 times 12 is 144 watts. Okay, because energy is neither created nor destroyed, transformers are assumed to be pretty close to 100% efficient. Well, I could actually figure out what my current is on this side using the power equation and knowing that I have 144 watts going in, going out. So I have to have 144 watts going in. P is equal to I times E. It's equal to I times 120 volts on that side. And then my I is 1.2 amps. So if I have 1.2 amps over here and 12 amps over here, notice my voltage changed by a factor of 10. And my current also changed in the other direction by a factor of 10. So here's the other cool thing about transformers. Let's say that I didn't care what was on the other side. All I know is that by Ohm's law, I have 120 volts going in at 1.2 amps. What does Ohm's law say? E equals I times R. What is my resistance? E, I, R. I don't know the resistance. R is equal to E divided by I is equal to 120 divided by 1.2. What is that?
10.
Well, it's not 10. 120 divided by 1.2.
100.
That's 100. My equivalent resistance is 100 ohms. My resistance changed as the square of my ratio. So not only can a transformer be used to transform voltage and transform current, it can also be used to transform impedance. This is known as an impedance match. We can use that as an impedance matching transformer. So let's say I had a transformer that looked like this, and I have a loudspeaker that is, let's say 8 ohms. And I have a 10-to-1 ratio on my transformer. What would it look like on this side? If I have 8 ohms times 100 is 800 ohms. It would look like I had an 800 ohm loudspeaker. So I could actually use that. Let's say if I knew that, I would actually have a circuit that would drive power into an 800 ohm impedance, and that would actually successfully drive my 8 ohm speakers. So that's what we use transformers for. Okay, so now we're doing transistors. Well, actually, let's do one more thing. Again, this is a diode. We have a special kind of diode that emits something. It emits light. This is a light emitting diode, or an LED. Everybody carries one of these on their phone. You turn the phone on. When you turn the light on the phone, it puts current through the diode and allows it to transmit light as a byproduct of it turning on. Okay, so now what we're going to talk about is something called the transistor. A transistor looks like this. Or this. And these are known as bipolar junction transistors, or a BJT. And they are 3-terminal devices. So notice that if you look at this, this is a diode and this is a diode, right? Each of them is actually kind of like 2 diodes squished back to back. And we draw a bipolar junction transistor like this. And we have one of them, because remember that a diode looks like this. It has an arrow. So obviously we need an arrow to make this representation look right. So what we're going to do is we're going to have an arrow. And this points out. So this is a PN. So this is obviously an N over here. This is called an NPN transistor. And the easy way to remember is that that arrow is not pointing in, because it's pointing out. If it's not pointing in, that's an NPN transistor. Now, if we were to reverse that arrow, that would be a PNP transistor. To be honest, most transistors for the sake of argument, are easier to look at as NPN transistors. The reason being that we have a plus here and a minus here, and that turns it on. And then we have a plus voltage here, and our channel goes that way. And then we have something down here called ground. Ground is our 0 reference point. So if we have a resistor here to protect it, and then a battery. So here's our ground. This transistor will have current flowing this way that will turn it on. When this turns on, the channel, this is known as the collector. This is the base, and this is the emitter. The base to emitter current, the base to emitter junction, when it's activated, will open up a big channel between the collector and the emitter. So a tiny amount of current from the base to the emitter allows a potentially very, very, very large current from the collector to the emitter. This can be particularly useful because let's say that we are running a light bulb. This is actually in the book with a big power supply over here. So we may have a very small power supply over here, which is just used through a switch, for instance. Let's use a push button. And over here, we have a big power supply, and that's a big transistor, so that when we push this button down, it closes the circuit, which then basically opens up this big channel and allows a lot of current to flow from the battery through the light and down to ground. So what this basically does is this is a remotely operated switch. The other use of a transistor is that we can do, okay, so that's basically saying that the transistor is going to be running full on and full off. Well, transistors actually don't always do that. If I have an input and an output curve for a transistor, at some point the transistor needs to have a certain amount of input. Yes, exactly like an aux light bar on a car. That you basically get to this point, and then no matter how much more you put in, the output gets to the point of diminishing returns. So there are actually 3 ranges here. This is known as cutoff, when it doesn't work at all. This is known as saturation, when it runs full open, and no matter how much more you put in, you can't do anything else. This very special sweet spot, literally right in here, where it's basically a straight line, is known as the linear range. And these three areas are used very differently. So if I were using a switch function, for instance, where I wanted something to be on or off, I would use this function and this function. Because if I'm halfway in between, who knows where it is? You know, I either want it all the way on or all the way off. This combination of stuff is typically used for digital logic, because in digital logic, we deal with things that are discrete, either on or off. This would be a 1 and this would be a 0. But that doesn't really do us any good if we're trying to amplify somebody's voice. One of the nice things about a transistor is that in this interior range, it's fairly linear, where a small change on the input will lead to a big and proportional change on the output. In this use, this is known as an amplifier. Notice it says linear amplifier. A transistor is a very good basis for something called a linear amplifier. But if it's driven into cutoff or driven into saturation, it's not linear anymore, and it doesn't work very well. So it's very important to use the transistor in the way that it will actually function properly in the way that you want it to. So there's another type of another type of transistor. Stupid Zoom. Another type of transistor, which you may actually recognize the innards a little bit. This is known as a field effect transistor, or a FET, and it has a gate and a drain and a source. Those are usually reversible. And what does this thing look like right there?
Capacitor.
That looks like a capacitor. Okay, so if I put pluses over here, what will happen on the other side? What will be attracted to it?
Minuses.
Minuses, and vice versa. So by just simply putting a voltage on this side, I can change what happens on the other side. And since I can do things like change this from pluses to minuses, and then I can make positives over here, basically by changing the voltage on this side, on the gate, I can actually change how the output behaves. And it's the same thing. It has the same similar type of curve where it has the cutoff and the saturation and the linear range. So a FET, or field effect transistor, can be used as an amplifier in this range, or for digital circuits by using those ranges on the outside. The cool thing about a FET is that how much current is actually being used to make it work on the inlet side. Once I charge up the capacitor, what happens?
Exposes over.
Yeah, it's just no more to go into it. All I have to do is change the voltage on the inlet side, and that changes what happens on the outlet, which is very, very efficient because it uses almost no current. That's why these are very, very popular for use in computers, because nobody wants a computer that has a giant power supply and gets really, really hot, especially a laptop. Nobody wants that. Everybody wants, more efficient devices like, their iPhone. What if your iPhone, every time you used it, got up to 250 degrees? I don't think you'd use it very much, right? And the battery life was 10 minutes.
On your diagram, what was S and D?
It's a gate, source, and drain. So if I draw my FET again, so this is the gate, and this is the source, and this is the drain. And those are often reversible.
And that was a field effect transmitter?
That is a field effect transistor.
Transistor, thanks.
Because internally there's an electric field that makes it work. And that's why it's a field effect. Okay, let's see, where are we now? Let's see. Circuit diagrams and schematics, amazingly, I'm going to say that in doing a little demonstration, I think we already kind of covered this, which is awesome. So everybody recognize that circuit that we already built?
Yeah.
Okay, that's a remote switching device. And part of it is element 1. They'll ask, for instance, what element 1 is. That's a resistor. Element 2 is what kind of transistor?
That's bipolar. Bipolar.
Bipolar junction transistor. It has 3 terminals. They're the collector, emitter, and base. Element 3 is a light bulb, and element 4 is a battery. And how about that element 5? Remember what that's called? That's ground.
Ground.
Ground is our 0-volt reference point. Okay, and how about this one, which we kind of already built? Remember what this one was?
This is the fuse.
Simple power supply, right? And how about item number 4 on this drawing?
That's the transformer.
That's a transformer. And what's the function of a transformer?
To
Increase or decrease power supply?
In particular, what?
transforms
Voltage.
voltage and current.
Voltage and current. Yep. In particular, AC voltage. It transforms one AC voltage to another. And the other one that'll show up again item number 8. That's an
Rectifier.
LED.
That's a diode.
That's a light emitting diode.
Yeah.
Notice the arrows coming off of it. And number 9,
Resistor.
it's a resistor, but it's adjustable.
A
which makes it
variable resistor,
that makes
right?
it a variable resistor or a potentiometer or a pot.
What shows that, the arrow?
Yep. The
Are
arrow
the,
makes
are
it
the
adjustable.
arrows for a variable resistor always beginning into the schematic and then, or will you
No.
sometimes see them starting out of the schematic and going around?
A variable resistor can be drawn a couple of different ways. So like this is that's a pot. And this is a pot. They're both variable resistors.
Thank you.
And often the reason that they do that is because very often this is, kind of known as a wiper. And it literally wipes across the surface of the resistor, which is exposed. So that's why, so it's more of a physical representation.
Okay, thank you.
Okay, let's see. Component 3 in figure number 2. Okay, so let's talk a little bit about switches. That is a switch, component number 3. So what we're going to do briefly is draw a switch. That is a switch. All right, and this is known as a single pole. A pole is a circuit. Now, it can only be thrown one way. It can only be closed. That is a single throw. You can only throw it closed. Now, if I had a switch that looked like this, let me erase that part and erase that and erase that and had a circuit that looked like this. That's a single pole circuit because there's only one circuit, but that is a double throw. Because you could throw it either this way or that way. And that would be represented by an SPDT switch. That would be known as an SPDT. Now, let's say that I had another circuit that was ganged together so that these wiper arms were actually connected. And I had something that looked like this. Well, it's still double throw because I can still only throw it two ways, but now it's not single pole, it's two separate circuits. So it's a double pole because there are two circuits. And that would now be a DP DT switch by adding the second pole. Okay. All right.
Which of those is most like a light switch, Scott?
Yeah. Well, you can have a single pole light switch or a double pole light switch. You can also like have a three-way light switch, which is a double throw light switch internally.
The light switches don't go in one direction. They only open and close a circuit. They don't go to multiple.
Well, that's true.
Could you do me a favor and go back to figure T2 and just name all those numbered?
Okay. Who wants to go through and name them all? Okay. Number 1, that's a power supply. They drew it as a power plug. Oh, number 2. We didn't cover number 2 yet. Time to do number 2.
It's a diode.
No, it's not. Here we go. Component number 2. It looks like this internally. This is actually very important. So let us say that this had a marking which was 10 amps on it. This is known as a fuse. The job of a fuse or a circuit breaker is such that if I have a voltage connected to here, and by Ohm's law, if I see that a current of, let's say, 12 amps is going to flow through the circuit, what will happen to the fuse?
It'll blow.
It will blow because this wire internal to it has been specified to have a certain gauge and resistance such that if anything greater than 10 amps flows through it, it will get hot and melt. So When you blow a fuse in your car, or you blow a fuse in the circuit breaker, or pop a, or you have a circuit breaker that pops in your fuse box, this is exactly why it happens. So the question is, what is this fuse used for? It is to protect all this stuff downstream. Because let's say that I had a resistor down here. Let's say this was a heater circuit, and something happened in my heater circuit, and this heater was suitable to run 8 amps. And the documentation said use a 10 amp fuse to allow for a little bit of an excursion. And something happened to the heater circuit, and all of a sudden it started pulling 14 amps. Well, if I am a good engineer who wants to save money and make my company happy, how much current is this wire going to be able to carry? If this normally only draws 8 amps, am I going to use a wire that's capable of carrying 20 amps? No, because that costs more money. So this wire would be capable of carrying 10 amps. And this wire would be capable of carrying 10 amps. And this wire would be capable of carrying 10 amps, because why would I spend more money than I had to? So what would happen if I had a malfunction and this resistor, which was also capable for typically drawing 8 amps and was putting out heat, suddenly started drawing 14 amps? What would happen to this circuit?
The fuse won't blow and
The
the
fuse would
circuit.
blow. That's right. Now, what would happen if I went in and I said, well, the fuse is blowing, I'm going to replace this with a 20 amp fuse? What would the end result be?
Melt the wires.
The
Or-
wires would burn off.
Or
The circuit would.
or the resistor would get really, really hot, or the wires would get really, really hot and catch fire. Or if they're in the wall, for instance, the wires in the wall might catch fire. And what's the end result of that?
House would catch fire.
You burn your house down. That's right. So that is why it's a good idea to always use the same fuse that came out of a circuit that was designed for the circuit.
What determines how much amps those wires can hold?
It's defined by the resistance of the wire. So
The
if I let's say, and also so the gauge. Let's also say that there is a circuit that it says either use number 8 copper or number 6 aluminum. The smaller the number, the bigger the wire. Number 6 gauge is bigger than number 4 or number 8. Why would I use that? Because aluminum is as good a conductor as copper. So I would need to use a bigger conductor. Now, aluminum's also special because aluminum oxidizes, and if you don't treat the surface correctly, you'll start a fire. Okay, circuit shown is a simple power supply. Component number 2 is a fuse. Component number 3 is a switch. Number 4 again is a transformer. 5 is a single diode. Again, the cathode is the banded end, which is on the right-hand side. 6 is a little bit of a curly looking capacitor. Sometimes you can have a different kind of capacitor, which is called an electrolytic capacitor. Somebody mentioned about blowing capacitors up. If you hook up an electrolytic capacitor, they have a plus and a minus sign on them. And if you hook them up backwards, you'll blow it up. Number 7 is a resistor. 8 is a light emitting diode, or an LED, which functions as an indicator saying the power is on. So here's a question. Why is there a resistor right next to the diode, right next to the LED?
Keep the voltage under the limited point.
Well, to keep the current, an LED typically draws about 3, 5, 10 milliamps. But once it's turned on, it'll take as much current as you can give it. So that resistor is basically there to intentionally limit the current and protect the diode.
You see them flash up.
Protected from what?
What?
Protect the diode from what?
Oh, from blowing up. because an LED is really, really tiny. And it's only made to pull usually like, 10 milliamps to light up. But internally, if you hook up a diode, once it's on, it's really on. So once it's conducting in the forward direction, that thing is turned on. So unless you have something to limit the amount of current going through it, it'll just, you'll put 10 amps through it for a very short time. It'll get really, really bright for like a millisecond. And then it won't work anymore.
Nope.
I know this because does everybody remember Radio Shack? I used to buy a pack of 100 LEDs in one pack. And I'd hook them up to like a 9-volt battery. And before I understood what biasing resistors, current limiting resistors were, I killed a lot of LEDs that way. It's too bad that kids can't go to Radio Shack and buy stuff like that anymore. But we do have Amazon. So
If you have a lightning strike close by, all the LEDs blow.
it's the same thing. Yeah, exactly. Ohm's law always wins. Item number 9 is a variable resistor used as a current limiter and a voltage limiter. And item number 10 is again a Zener diode. Notice if you turn your head sideways, that thing on it kind of looks like a letter Z. That's a special diode called a Zener diode, which operates in the backwards direction, and it serves to limit voltage. Go ahead.
I just said thank you.
Oh, yeah. Okay, so one more circuit, and then we're going to call it for the day. And here we go. One more circuit, which is this right here. And so what do you see in this circuit? Number 4 is an antenna. And what are those two funky looking capacitors?
Spots, right?
Yeah, what are those funky looking capacitors?
Variable
They're
capacitor.
variable capacitors. And how about number 3?
Transformer.
Yeah, nope.
That's
Just an
variable.
inductor. But what do you notice about the inductor?
Variable.
That's variable. Yeah. And why would that be? Why would you ever need to do that? I mean, what a weird looking thing, right?
Tuning radius.
Tuning. Yeah. Okay. So what I'm going to show you is the guts of something called a tuning circuit. Okay. So inside this device, let me click on this, see if I can make it bigger. Oh, that's not helpful at all. There we go. That's helpful. Okay. On the left-hand side, those are capacitors. And notice they have a bunch of parallel plates. They turn. And a capacitor is basically parallel plates. That's what a capacitor is. By turning them, they either mesh or unmesh, which changes the amount of capacitance between the plates. So fully meshed, that's maximum capacitance, and fully unmeshed is minimum. On the right-hand side, what you have is an inductor, and it's not continuously variable, but notice that it's connected by wires to a switch, a whole bunch of different wires. Those different wires short out part of the inductor and make that part of the inductor useless, basically because it's shorted out. By doing that, you change the amount of coil that's then exposed, which changes the inductance. And the reason that you would do something like this is because if we look at what's on number 4 here, number 4 is an antenna which has an impedance, which is, again, some value with an angle. And what do we know about capacitors and inductors? They are frequency dependent components. So by changing the value of the capacitor and by changing the value of the other capacitor and by changing the value of an inductor, what you can end up doing is taking a circuit that looks like this, which has a Z of a question mark, and combining it then with a capacitor, which is adjustable, which basically is now in series. Series inductances simply add. And now this is in parallel in a way. because this is the outside world at the end of the antenna, and this is the outside world. So this combination is now in parallel with this right here, which is ZL. And then this is now in series. This whole combination is now in series with this, which is actually a pretty complex mathematical thing. Now, the reason that we do this is because our transmitter is designed and happy when it sees an impedance of 50 ohms. And typically we want this to be purely resistive. So if we were to look at this on that graph, we would have our R, which is our resistance, and we would have our inductance and our capacitance going this way. We would want these to completely cancel each other. So we end up with this unknown antenna, which has resistance and some kind of reactance, X. So we use a combination of this capacitor and this inductor and this capacitor to basically make it so these all cancel out. So we end up with something that is 50 ohms. We can also make this arrow go in and out by using that. And by doing that, we can make our transmitter happy, which is really the goal of being able to put power out of a transmitter. If we have an impedance match of 50 ohms, pure resistive, then we have a happy transmitter. We have a good match in our system. And we will be covering that tomorrow. And I think that is all I've got for today. And tomorrow we've already covered tuned circuits. We already covered switches. A device that displays an electrical quantity as a numeric value is known as a meter. A whole bunch of things in one little block is known as an integrated circuit. All your resistors and capacitors and transistors, that's known as integrated circuit. And finally, if we have a wire carrying a current, what does a wire carrying a current make? What does a current
Resistant?
make?
Resistant?
Makes a loop around it. Magnetic field. Okay.
Yes.
Now, if we take another wire and we stick it in the magnetic field, what gets made?
Electric current.
Another current. So a current makes a magnetic field and a magnetic field makes a current. This is known as coupling. And what if those are microphone wires?
Feedback.
You get crosstalk and feedback and all kinds of bad stuff. So in order to prevent that, we use shielding. That's why we use, for microphones, we use shielded cable. The shield basically creates an environment surrounding the stuff on the inside that essentially catches the magnetic field and constrains it internally. So that's why we use shielded cable. And okay, so tomorrow, just looking at this, we already covered RF and stuff like that. Tomorrow we're getting into, oh, my favorite part. Tomorrow we're doing antennas.
Question.
Yes.
So when you have two walkie-talkies that come in contact with one another when you're speaking into one,
Yep.
we always called that feedback. Is that the correct term?
Well, I mean, if you talk about feedback, I mean, basically that's audio feedback. I would assume, right? If you have some output of one speaker getting back into the microphone.
Yeah, it'll go woo.
Yeah, that's audio feedback.
Okay.
But now you can also have RF feedback where a transmitted signal, because every piece of wire can act as an antenna. If you have a transmitter putting out something into space, and you have a piece of wire, let's say hooked up to your computer, like a USB cable, you can get RF being conducted through that cable back into your computer. Anyone ever seen that happen? Anyone ever locked up a computer like that? I've done it a lot of times. Yeah. So there are special tools that we have for getting rid of that feedback situation where we are feeding RF back into our circuits. You know, computers don't like it when you have RF energy getting back into them. It never ends up well. I mean, if it's a monitor, the monitor can get all wavy. If it gets into the CPU, you can lock up your system. The first time I did that was 1988. I did that on my original PC. I used to do it all the time. I had a 2-meter packet transmitter, and whenever I keyed up, it would lock up my computer. And so what we do to prevent that is we take our cable and we wind it through something called a ferrite, which is basically it's like a donut that's made of glue and usually iron and nickel powder all baked together. So it's in the shape of a donut, and you run your cable through it a bunch of times. You've probably all seen one because it's impossible to get a power supply that doesn't have something that looks like this on it. Everybody's seen one of these, right? This is an RFI choke. Basically, it's powdered metal and glue that's baked into a shape so that if there's any RF energy floating around, if it tries to get conducted down the cable, DC does not get affected, but the magnetic field that is generated by radio frequency energy will kind of like spin out inside that material and just turn into heat, and thus be squelched out before it gets into the device.
You can buy them on Amazon for cheap.
Yeah,
Whole
I
bunch
have
of them.
I have dozens and dozens and dozens of them. They're useful for lots of different things.
Yeah.
Any other questions?
Yeah, when a radio wave is transmitted from an antenna, you have the horizontal component and the vertical component.
Mm-hmm.
I always thought that they twisted around, following the right-hand rule radially from the antenna. Is that not true?
They are always following the right-hand rule, but there's no guarantee. There's nothing saying they have to be rotating. If it's a plane wave, they stay constant. You can have a rotating polarization, which rotates over time, or you can have it be static, depending on how you build it. I mean, actually, and it's much more common for it to be static. Now, they both oscillate continuously at the frequency you want them to, but the polarization typically stays the same. Drew, your hand's up. Very polite. Uh-oh. Drew, you there?
Maybe he'll say bye.
Oh, maybe so. Any other questions? Is everybody still doing okay? That's a lot of material. Everybody studying?
Hopefully.
All the, I think that hopefully, if even half of it, if even 10% of it sticks, you're doing well. I've spent an entire lifetime doing this.
I'm trying to be polite. Can you hear me okay?
Yep.
I was sending you a message. It's just in an area where I can't talk a whole lot, but the question was, can you ground shielding to say like your ground wire in your house to do the similar to what a ferrite would do?
Great question. And the answer is it depends on the wavelength that you're trying to ground. Grounding is something that we're going to cover in the next day or so. And the easiest way to describe grounding is, let's say that you have ground down here, right? And here's your house, or here's your equipment, and there's a cable that is, let's say, 60 feet. to get to ground. At 60 hertz, what is the wavelength? Because 60 hertz has a wavelength. $5 million meters or 5,000 kilometers. How long is 5,000 kilometers? That's like from the West Coast to the East Coast. So basically ground at for power, ground is ground. For power. But now here's the other question. Let's pick an RF frequency. Let's say that we're dealing with 30 megahertz. Wavelength is 10 meters. That's 33 feet. You have it right here. What is that law? What is that 60-foot piece of wire? What is it now? It has a name.
Antenna.
That's called an antenna. That is now called an antenna. That will pick up energy and that will radiate energy. So RF ground is not equal to power ground. And that's why RF ground can be really tricky. Because, you know, power ground is safety ground. RF ground is RF ground. You know, they're totally different things. They behave differently.
Cool, thanks. So do they use that for the purpose of trying to, I mean, the point of ground is to, in electrical wiring of a house is obviously different. They're looking to, oh, whoops, current is running through here. Let's send it a different direction, like when lightning strikes your house.
Mm-hmm.
But is there a potential where they use that for any kind of RF shielding when it comes to
I mean, that's the whole
wiring, or
purpose.
no?
That's the whole purpose. Having done this before, let's say you lean in to talk into your microphone, you key the radio and you lean in and you get an RF burn on your lip. Done it.
Mm-hmm.
And that's because it was, 50 or 60 feet from where my equipment was to the ground where the water pipe went into the ground. I was on the second floor. So what is the case? Literally, what is the case of my equipment? What voltage is it at? Ideally, it's at 0 volts, right? At least 0 volts RF. It was at 0 volts, at 120 volts at 60 hertz. But with all that wire, how much voltage was there on my, on that microphone and on the chassis? And it was, a lot of volts of RF, which was enough to give me an RF burn on my lip. I got a nice shock from it.
An antenna burns on the boat.
Oh yeah, they feel great.
Mm-hmm.
It makes a little pinhole in your hand. If you touch a wire that's carrying RF, yeah, it hurts like a lot.
Mm-hmm.
All right. I hope everybody's still doing okay. I hope everyone's still having fun. I hope if you got questions, you should ask them. And Pablo, what happened to that car that's on its side?
Drove it.
Whose car was that?
My car.
Did it survive that?
Oh yeah.
Yeah. Okay.
Yeah, we raced it for a lot of years after that, but that was a good rollover.
What is it? A WRX?
Indeed.
Yeah.
Yeah, I just wanted to add, I subscribe to the Dirtfish School emails, and it's good to see you guys on here.
Say Dirtfish?
Yeah, Dirtfish Rally School.
Yeah, it's a